Hello there, and welcome to Midnight Geography. Tonight, we'll drift into the quiet geography of Indiana. Indiana is a land where ancient seas left their memories in stone, where glaciers carved their final signatures before retreating north, where rivers found pathways through limestone labyrinths that still flow in darkness beneath farms and forests. It is a place where the earth's patient work reveals itself in gentle undulations, in hidden caves, in the slow accumulation of soil over millennia. Indiana is geography's whisper rather than its shout, a testament to how the planet shapes itself when given time, when given water, when given the weight of ice that came and went. If you enjoy these peaceful geographical explorations, consider liking and subscribing. It helps other curious minds find their way here too. But for now, let's begin. Along the southern shore of Lake Michigan, within what is now Indiana Dunes National Park, there exists sand that sings. Not metaphorically, but actually produces audible tones when walked upon. The sound emerges from quartz grains so perfectly rounded by millennia of wave action that they possess an almost crystalline uniformity. When pressure is applied, a footstep, a hand brushing across the surface, these grains slide against one another with such precision that they vibrate at frequencies the human ear can detect. The phenomenon occurs only when conditions align. The sand must be dry, the grains must be of nearly identical size, and the quartz itself must possess that particular roundness that only time and water can create. Ancient Lake Michigan, larger than its current form, spent thousands of years tumbling these grains, polishing away every irregularity, creating an instrument that would wait in silence until someone walked across it. The sound itself has been described as squeaking, humming, sometimes almost like distant music carried on wind. It is the song of deep time, performed by minerals that remember when this shoreline lay elsewhere. The highest point in Indiana rises in Wayne County near the Ohio border at a place called Hoosier Hill. At 1,257 feet above sea level, it barely qualifies as a hill by the standards of mountain states. And yet, this modest elevation represents something profound about Indiana's geography. Its essential flatness, its character as a place where the land rolls gently rather than thrusts upward. Stand at Hoosier Hill, and you perceive no dramatic vista, no commanding view of distant ranges. Instead, you see forest and farmland extending in soft undulations, the landscape shaped more by what covered it than by what pushed through it. The glaciers that advanced and retreated across this region worked as levelers, grinding down whatever prominence might have existed, filling valleys with till, creating a terrain where even the highest point feels humble. This is geography without arrogance, land that makes no grand claims. The earth here simply exists at a particular elevation, neither apologizing for its modesty nor compensating with drama. In a way, Hoosier Hill embodies Indiana itself, quietly present, unassuming, shaped by forces that passed through and moved on. Beneath the forests of Harrison County, in darkness that has persisted for thousands of years, limestone formations grow with patience that defies human comprehension. Marengo Cave extends through this underground realm, its chambers adorned with stalactites that have accumulated calcium carbonate one molecule at a time. The mathematics of their growth reveals something beautiful about geological time, approximately 1 inch per century. Consider what this means. A stalactite measuring 40 inches descended through 4,000 years, drip by infinitesimal drip, each molecule of dissolved limestone carried by water seeping through rock, deposited as the water released its carbon dioxide into cave air. While human civilizations rose and fell above While forests grew and were cleared and grew again, these formations lengthened in absolute darkness, following chemical imperatives that care nothing for the urgency of surface life. Some formations in Marengo Cave have been growing since before the last ice age, since before humans populated this continent. They continue growing now at this very moment, adding layers so thin they cannot be measured in human timescales, only in centuries. The cave itself remains cool and silent, a space where time moves differently. In Orange County, a river disappears. Lost River flows above ground like any ordinary waterway, moving through its valley with the meandering patience common to lowland streams. Then, without ceremony, it simply vanishes. The riverbed continues, but the water is gone, pulled underground through dissolution channels in the limestone bedrock. For 23 miles, Lost River flows through passages carved over millions of years, through caverns humans have never seen, following gradients and pathways mapped only by the water itself. The surface valley remains, a ghost of the river's former course, dry except during exceptional floods when the underground channels cannot accommodate the volume and water spills back into its old bed. Eventually, near the east fork of the White River, Lost River returns. It emerges at a place called the Rise, water that has traveled in darkness now rejoining the visible world. The fact that this occurs, that a river can simply vanish into stone and re-emerge miles away, speaks to the nature of limestone, to its solubility, to the patient work of water dissolving rock grain by grain until entire rivers can pass through the bedrock. The Wabash River stretches 503 miles across Indiana, making it the longest free-flowing river east of the Mississippi that remains entirely within a single state. Free-flowing means no major dams interrupt its course, no human intervention fragments its continuity. The Wabash begins as a modest stream in Ohio, crosses into Indiana, and grows through the accumulation of tributaries until it becomes the substantial waterway that marks Indiana's western boundary. Its watershed drains much of the state, collecting water from thousands of smaller streams, creeks, and rivers, channeling rainfall from forests and fields and cities toward its eventual confluence with the Ohio River. The name Wabash derives from a Miami, Illinois word meaning pure white, possibly referring to the limestone bedrock over which it flows in places, or perhaps to the way sunlight reflects from its surface. Indigenous peoples lived along its banks for thousands of years before European settlement, finding in the river both sustenance and transportation. The Wabash has witnessed enormous change. Forests cleared, cities built, agriculture transforming the landscape. Yet the river itself continues its work of moving water from high ground to low, following pathways established when glacial meltwater first carved its valley. Deep beneath the city of Jeffersonville, far below streets and buildings, lies a window into an ancient world. The Jeffersonville Limestone Formation, 380 million years old, preserves a complete Devonian coral reef ecosystem in stone. During the Devonian period, this region lay beneath a warm, shallow sea, its waters clear and tropical, its seafloor home to organisms that built elaborate calcium carbonate structures. Corals grew in colonies, their polyps extracting dissolved minerals from seawater to construct protective skeletons. Brachiopods filtered nutrients from the water. Crinoids, sea lilies, swayed with currents on their stalks. Then conditions changed. The sea withdrew, sediment buried the reef, and over millions of years, pressure and chemical processes transformed soft seafloor mud into solid rock. The organisms themselves became fossils. Their original material replaced molecule by molecule with minerals, preserving form without preserving substance. Today, the Jeffersonville limestone is quarried for construction, and in doing so reveals this ancient reef, its structure so well preserved that paleontologists can identify individual species, can reconstruct the ecology of a world that existed before trees, before insects evolved flight, before anything resembling modern life populated the land. At Indiana Dunes National Park, Mount Baldy moves, not metaphorically, but literally migrates inland at approximately 4 feet per year. This living dune, standing 126 feet high, advances through a process both simple and inexorable. Wind from Lake Michigan carries sand up the windward slope, deposits it at the crest, and the grains tumble down the leeward side, pulled by gravity. Grain by grain, the entire dune shifts inland, consuming whatever lies in its path. Trees that once grew in front of Mount Baldy now stand buried beneath tons of sand, their trunks preserved in the darkness under the advancing dune. Historical photographs show the dune in different positions, its migration documented across decades. The phenomenon creates an odd temporal awareness. This is not landscape as static backdrop, but landscape as active process, geography in motion. Local residents have watched the dune approach structures, have seen it gradually overtake parking areas and paths. Eventually, Mount Baldy will migrate far enough inland that Lake Michigan will deposit new sand in the space it vacated, beginning the cycle again. The dune is both ancient and constantly new, its sand recycled from glacial deposits, its form never fixed, always moving. In the town of French Lick, mineral springs have bubbled to the surface for more than 10,000 years. The water emerges from deep aquifers, having percolated through layers of limestone and other sedimentary rock, dissolving minerals as it descends and then rises back toward the surface. A geological fault line beneath French Lick creates a natural pathway for this water, allowing it to reach the surface rather than remaining locked underground. The springs were known to indigenous peoples long before European settlement, valued for the minerals they contained and the consistent temperature of the water. Later, these same springs attracted settlers who built resorts around them, marketing the mineral water as therapeutic. The springs themselves remain constant, flowing at temperatures that vary little throughout the year, their chemistry reflecting the rock through which the water has traveled. Sulfur, calcium, magnesium, iron, all dissolved from bedrock during the water's underground journey, then released at the surface where the water finally reaches the air. The fact that these springs have flowed continuously for millennia, unchanged by human presence or absence, offers a certain comfort. While everything else shifts and transforms, the springs continue their quiet emergence. Brown County's Weed Patch Hill creates a climatic anomaly visible in the plant life that grows there. The hill's north-facing slopes remain cool and moist, even during summer heat, creating conditions similar to regions 200 miles north. This microclimate supports plant species ordinarily found in colder latitudes, species that would not survive in the surrounding lowlands. Meanwhile, the south-facing slopes receive more direct sunlight, warming to temperatures that support southern plant species rarely found elsewhere in Indiana. The result is an almost impossible botanical convergence. Northern and southern flora existing within yards of each other, separated by slope aspect and the few degrees of temperature difference that creates. Ecologists find in Weed Patch Hill a compressed illustration of how climate shapes biology, how even subtle differences in exposure and elevation create distinct worlds. The plants themselves care nothing for biogeographic boundaries. They simply respond to the conditions they find. A hemlock that would thrive in Michigan finds suitable habitat on one slope. A southern species adapted to Kentucky's climate survives on another. Between them, the full range of Indiana's transitional forest demonstrates how geography creates complexity through the simple interaction of sunlight and topography. Morgan Monroe State Forest contains a spring of startling clarity and abundance. The Great Blue Spring discharges 250 gallons per minute, a constant flow emerging from an underground aquifer whose full extent remains unmapped. The water appears at the surface at 53 degrees Fahrenheit, a temperature it maintains regardless of season. In winter, when air temperatures plunge below freezing, the spring water feels warm by comparison, its relatively constant temperature creating mist in the cold air. In summer, when surface water heats under the sun, the spring's 53 degrees feels cool, almost cold. This consistency reflects the aquifer's depth and the Earth's own temperature gradient, deep enough that seasonal variations never penetrate, shallow enough that the water emerges at drinkable temperature rather than the scalding heat of true geothermal systems. The spring has carved its own small canyon over millennia, the constant flow eroding soft soil and occasionally undermining rock. Moss grows on stones, kept perpetually wet by spray. The sound of water fills the space, a white noise that seems to absorb other sounds, creating a pocket of acoustic isolation. No one knows exactly where this water originates, what recharge area feeds the aquifer, how long the water spends underground before emerging here. The spring simply flows as it has flowed for thousands of years. 400 million years ago, Indiana did not exist as dry land. Instead, a shallow tropical sea stretched across this region, its waters warm, its seafloor accumulating sediment carried from distant mountains. The sea extended from what would become the Appalachian region westward toward what would become the Rocky Mountains, covering the interior of the continent. Marine life flourished in these shallow waters. Corals, brachiopods, crinoids, trilobites, countless organisms whose names we know only from fossils. The climate was tropical because continental drift had positioned this landmass nearer the equator. Coral reefs grew in formations similar to modern Caribbean reefs, their structure and ecology recognizable across 400 million years of evolutionary change. Then, slowly, the sea withdrew. Tectonic forces lifted the land, or sea levels dropped, or both processes occurred simultaneously. The shallow seafloor became exposed land. Organisms that had lived in water died, were buried, and over immense time transformed into fossils embedded in rock. Today, Indiana's limestone formations contain the evidence of that ancient sea. Fossils so abundant that a single rock face can reveal hundreds of organisms, their forms preserved in stone that was once soft mud on a tropical seafloor. The limestone itself consists largely of calcium carbonate from marine organisms, the accumulated skeletal material of creatures that lived and died in warm waters that covered what would eventually become Indiana. In the bottomlands along the Muscatatuck River, cypress swamps create landscapes unexpected in Indiana. Bald cypress trees grow with their roots in standing water, their trunks flared at the base, their knees, specialized root projections, emerging above the water's surface. These are trees associated with the Deep South, with the swamps of Louisiana and Florida, not with the Midwest. Yet here, they thrive in isolated pockets, remnants of a time when Indiana's climate was warmer, wetter, more southern in character. The last ice age never covered this southeastern corner of Indiana, allowing these refugia, these ecological pockets, to persist. As climate cooled and glaciers advanced farther north, the cypress remained, adapted to local conditions, their seeds producing new generations that continued the population. Now, thousands of years after the glaciers retreated, these cypress swamps endure as living connections to a different climatic era. Stand among them in late summer when water levels are low, and you might briefly imagine yourself in bayou country. The trees themselves seem out of place only because human lifetimes are too short to witness climate's natural fluctuations. To the cypress, this is simply home, as it has been for millennia. Beneath the farmland of Newton County lies the ghost of an enormous wetland. The Great Kankakee Marsh once covered 500,000 acres across northwestern Indiana and northeastern Illinois, a vast network of channels, sedge meadows, and open water. Early settlers described a wetland so extensive that crossing it by wagon required 2 full days of difficult travel. The marsh supported incredible biodiversity, waterfowl by the millions, fish in staggering abundance, mammals and plants adapted to life in a landscape where water was the dominant feature. Then, beginning in the late 19th century, systematic drainage commenced. Engineers dug channels, straightened rivers, installed tile drains beneath fields. The goal was agricultural land, and the project succeeded spectacularly. Where water once stood, crops now grow. The fertile soil that had accumulated in the marsh, organic material built up over thousands of years, proved exceptionally productive. Today, only fragments of the Great Kankakee Marsh remain, preserved in nature reserves that protect small portions of what once stretched to the horizon. Yet even drained, the marsh's influence persists. The soil remains rich. The hydrology, though altered, still reflects the underlying topography that once created such extensive wetland. And in the remaining fragments, you can glimpse what existed before drainage, can imagine the scale of what was lost and what the land once was. The Ohio River descends 430 feet in elevation as it forms Indiana's southern boundary, a gradual drop that creates varying current speeds, and, in places, rapids where harder rock resists erosion. Near Louisville, the river once plunged over ledges in a series of falls and rapids that made navigation impossible during low water. These falls of the Ohio represented a natural barrier to river traffic, a place where boats had to be portaged or cargo unloaded and transported around the obstacle. The falls existed because of resistant Devonian limestone, rock that eroded more slowly than surrounding material, creating a ledge over which the river tumbled. Modern dams now control the river's flow, and the rapids are submerged except during exceptional low water. But the underlying geology remains unchanged. The river continues its work of eroding rock and moving sediment, processes that will eventually erase these falls entirely, given enough time. But that time is measured in millennia, perhaps millions of years. For now, the falls exist in a kind of suspended state, drowned by human engineering yet still present beneath the surface, waiting for water levels to drop and reveal them once more, exposing rock that has channeled the river's flow for countless thousands of years. Portland Arch Nature Preserve contains a natural bridge, a span of limestone 40 feet wide, where a creek has carved entirely through solid rock. The arch formed through a process called stream piracy and dissolution, water finding a weakness in the stone, exploiting it through chemical erosion, gradually enlarging a passage until an entire creek could flow through. Eventually, the passage grew large enough that the creek abandoned its surface course and flowed through the arch permanently, leaving the rock span exposed above. The formation is not unique. Similar features exist wherever limestone and water interact over sufficient time. But each natural bridge represents millions of years of patient erosion, water dissolving stone molecule by molecule, grain by grain, until solid rock contains voids large enough to walk through. Stand beneath Portland Arch, and you perceive both the accomplishment and its insignificance. Water has carved through 30 or 40 feet of limestone, yet the rock layers extend hundreds of feet deeper, representing time periods so vast that the arch's age becomes almost trivial by comparison. The creek continues flowing, continues eroding, will eventually undermine the arch itself and bring it down, creating a new valley where the bridge once stood. Across Indiana, a diagonal line separates two distinct landscapes. North of this line, the terrain is predominantly flat, the result of glacial action that ground down pre-existing topography and deposited thick layers of till. South of the line, the land becomes noticeably hillier, with valleys carved by rivers, ridges covered in forest, topography that reflects bedrock structure rather than glacial deposition. This boundary marks the Wisconsin Glacier's terminal moraine, the farthest extent of the ice sheet that advanced across North America during the most recent glaciation. The glacier reached this line and advanced no farther, either because climate warmed or because the rate of melting equaled the rate of advance. Here, at its terminus, the ice deposited enormous quantities of rock, soil, and debris scraped from the landscape farther north, material carried in the ice and dumped when the ice melted. The moraine itself forms a ridge in places, a subtle rise in elevation marking where the glacier stopped. But its significance extends beyond topography. It represents a boundary between geological provinces, between landscapes shaped by ice and landscapes that escaped glaciation. Everything north of this line was covered by ice thousands of feet thick. Everything south remained ice-free, though the climate there was surely colder, its ecology altered by the ice sheet's proximity. Clifty Falls State Park preserves 4 waterfalls that drop between 60 and 80 feet over ledges of Silurian limestone. Each fall occurs where a creek reaches a resistant layer of rock, a ledge that erodes more slowly than the softer stone below it. Over time, the force of falling water undermines the ledge, sometimes causing sections to collapse, gradually moving the falls upstream as the process repeats. The limestone itself formed 400 million years ago in the Silurian period, when this region again lay beneath a warm sea. Marine organisms, primarily coral and brachiopods, built reefs and shells from calcium carbonate. When the sea withdrew, these accumulations of biological material lithified into the limestone that now forms the waterfall's ledges. The water cascading over these falls has been falling for thousands of years, longer than human memory, longer than recorded history. Each drop of water carries a minuscule amount of dissolved limestone, removing the fall's substance atom by atom. Given enough time, tens of thousands, perhaps hundreds of thousands of years, the falls will erode completely, the ledges disappearing, the creek establishing a more gradual gradient. But that future remains distant. For now, the water falls with a roar audible from hundreds of yards away, mist rising from the plunge pools, creating microclimates cool and damp even on hot summer days. In the darkness beneath southern Indiana, evolution has created transparent creatures. Cave crayfish, specifically species adapted to subterranean environments, have lost all pigmentation, their bodies colorless, their internal organs visible through translucent exoskeletons. They have also lost their eyes, useless organs in perpetual darkness, eliminated through countless generations of genetic drift and natural selection. These crayfish navigate limestone caves by touch and chemical sensing, detecting vibrations in water, following scent trails to food sources. They have lived in these caves for at least 50,000 years, perhaps longer, isolated populations each adapting to their specific cave system. Food is scarce in caves. No photosynthesis occurs in absolute darkness, so all energy must enter from the surface through infiltrating water, through organic material washed in during floods, through the occasional animal that ventures underground. The crayfish are opportunistic scavengers, consuming whatever becomes available, surviving in an environment where resources arrive unpredictably. Their metabolism is slow, their growth rates measured in years rather than months. Some individuals may live for decades. They exist in a timescale entirely foreign to surface life, where seasons don't exist, where temperature varies by only a degree or two year-round, where light never penetrates. These are creatures shaped by darkness and stone, and the patient work of adaptation across millennia. Lake Wawasee, covering 3,410 acres in northeast Indiana, is the state's largest natural lake. Natural is the significant qualifier. Larger reservoirs exist, but they are artificial, created by damming rivers. Lake Wawasee formed through a specific glacial process. As the Wisconsin Glacier retreated, massive blocks of ice separated from the main ice sheet and became buried in sediment. These ice blocks persisted for years, perhaps decades, slowly melting within their sediment covering. As they melted, the ground above them collapsed, creating depressions that filled with water. These kettle lakes, named for their characteristic bowl shape, dot the glaciated landscapes of North America. Lake Wawasee is simply the largest such feature in Indiana, a depression carved not by running water, but by the negative space of vanished ice. The lake bottom contains sediment that dates back thousands of years, recording changes in climate, vegetation, and land use through the accumulation of pollen, organic material, and mineral particles. Core samples from the lake's deepest points preserve this record, allowing scientists to reconstruct the lake's history from its formation to the present, reading the layers like pages in a book written by the Earth itself. The Knobstone Escarpment stretches 150 miles across southern Indiana, a ridge system that rises 400 feet above the surrounding terrain. To call it a mountain range would be generous by the standards of the Rockies or Appalachians. Yet in the context of Indiana's generally subdued topography, the escarpment provides something approaching dramatic relief. The formation exists because of differential erosion. The cape rock atop the ridge consists of harder sandstone that resists weathering more effectively than the softer shales and limestone surrounding it. Over millions of years, streams and rivers carved away the less resistant material, lowering the adjacent valleys while the escarpment remained elevated. The result is a landscape of steep-sided hills and narrow valleys, terrain that contrasts sharply with the flat agricultural lands to the north. Hikers on the Knobstone Trail traverse this ridge system through forest that has reclaimed land once cleared for farming. The path climbs and descends repeatedly, each ascent revealing views across forested valleys that extend to distant ridges. In autumn, when hardwood leaves turn color, the escarpment becomes a ribbon of red and gold winding through the landscape. But even in winter, when trees stand bare, the underlying structure remains visible. Stone layers tilted at angles, erosion exposing geological history, topography revealing the Earth's patient process of removing material grain by grain, century by century, until only the most resistant rock remains elevated. Beneath Blue Spring Caverns, a river flows in absolute darkness. Not a stream, but an actual navigable river wide enough and deep enough to support boats that carry visitors through passages carved through limestone over immense time. The underground river extends for more than 5 miles through explored sections, though additional unmapped passages almost certainly exist. In this perpetual darkness live blind cavefish, their eyes vestigial or absent entirely, their bodies colorless, their navigation dependent on lateral line organs that detect pressure changes in the water. These fish have never experienced light, nor have their ancestors for thousands of generations. The water itself remains at a constant 52 degrees Fahrenheit year-round, fed by aquifers that buffer seasonal temperature changes. The river's course follows dissolution channels in the limestone, passages that began as hairline cracks and enlarged over millennia as slightly acidic groundwater dissolved calcium carbonate. In some sections, the ceiling rises dozens of feet above the water. In others, it drops so low that boats must navigate carefully to avoid collision. The darkness is complete, not the darkness of a moonless night, where eyes eventually adjust, but the absolute absence of light that exists only underground or in the deepest ocean. It is darkness as a physical presence, something almost tangible. And through this darkness, the river flows as it has flowed for thousands of years, moving water from aquifer to eventual emergence, following gradients that care nothing for human presence or absence. The Tipton Till Plain covers most of central Indiana, with glacial deposits that reach 300 feet thick in places. Till is the unsorted material left behind when glaciers melt, a mixture of clay, sand, gravel, and boulders all deposited together, whatever the ice happened to be carrying when it finally released its load. The Wisconsin Glacier advanced across this region 18,000 years ago, grinding bedrock into powder, plucking boulders from the landscape, transporting material hundreds of miles from its origin. When the ice melted, all this material dropped onto the landscape, burying pre-existing topography beneath layers of sediment. The resulting plain is remarkably flat, with slopes so gentle that drainage becomes difficult. Before settlement, much of the Tipton Till Plain consisted of poorly drained prairie and wetland. Settlers who arrived in the 19th century found extraordinarily rich soil. The ground-up minerals from glacial action had created one of the most fertile agricultural regions on Earth. Today, corn and soybeans grow where prairie once stretched to the horizon, but the productivity of the land reflects its glacial origin. Below the soil, the till extends down and down, sometimes hundreds of feet, burying river valleys that existed before the Ice Age, filling depressions, leveling an ancient landscape. Drill deep enough and you eventually reach bedrock, the original surface on which the glacier traveled. But between that bedrock and the modern surface lie these thick deposits of till, the glacier's final gift to a landscape it both destroyed and renewed. At Shade State Park, Sugar Creek has carved canyons 100 feet deep through sandstone that predates the dinosaurs. The rock itself formed approximately 300 million years ago during the Pennsylvanian period, when this region was a vast river delta draining into a shallow sea. Rivers deposited sand that accumulated in thick layers, eventually compressing and cementing into sandstone. Much later, long after the rock had solidified, glacial meltwater from the retreating ice sheets flowed across the landscape with tremendous volume and erosive power. Sugar Creek captured some of this flow, and the sudden increase in water volume allowed it to cut rapidly downward through the sandstone, carving narrow gorges with vertical walls. Today, these canyons create cool, shaded environments where ferns grow in profusion and ice persists into late spring. The canyon walls reveal the sandstone's internal structure, layers deposited one atop another, each representing a distinct period of deposition in that ancient river system. Some layers contain fossil plant material, carbonized fragments of vegetation that grew in the delta forests. Walking through these canyons, you move through geological time made visible, each step taking you past millions of years of accumulated sediment, past evidence of climates and ecosystems that existed before mammals, before flowering plants, before the continents themselves occupied their current positions. The creek continues its work of erosion, cutting fractionally deeper each year, grain by grain removing the evidence of that ancient delta. Deep beneath northern Indiana, far below the glacial deposits and bedrock, lies the Michigan Basin, a geological structure containing rock salt deposits 400 feet thick. These salt beds formed 400 million years ago when the region was covered by a restricted sea, a body of water connected to the ocean but with limited circulation. As climate warmed and evaporation exceeded inflow, the sea became increasingly saline. Eventually, salt began precipitating directly from the water, settling to the seafloor in thick layers of halite, rock salt. This process repeated through multiple cycles as sea levels rose and fell, creating alternating layers of salt, limestone, and other evaporate minerals. Over geological time, these deposits were buried under thousands of feet of younger sediment. Today, they remain deep underground, accessible only through drilling. The salt itself is remarkably pure, having crystallized from seawater, free of the pollutants and contamination that affect surface deposits. Some of these salt formations are mined through solution mining. Water is pumped down, dissolves the salt, and the brine is pumped back up for processing. The existence of these deposits reveals something fundamental about Earth's climate history: periods of intense evaporation, of seas that shrank and vanished, of climates warm enough to evaporate entire ocean basins. The salt preserves this history, a crystallized record of ancient atmospheric conditions, waiting in darkness thousands of feet below fields and forests. McCormick's Creek Canyon exposes rock layers tilted at angles that seem to defy the horizontal bedding normally associated with sedimentary stone. The strata stand at dramatic inclinations, some beds nearly vertical, as if some immense force folded solid limestone like fabric. This deformation occurred deep underground, when the rock was buried under sufficient pressure and temperature that it could bend rather than fracture. Tectonic forces associated with ancient mountain-building events compressed the rock, creating folds and tilts on scales ranging from inches to miles. Later, erosion removed the overlying material, exposing these tilted beds at the surface where water could carve through them. The result is a canyon where geological layers that should lie horizontal instead angle steeply, creating a visual puzzle for anyone trying to understand the landscape's history. Stand on the canyon floor and you can touch rock that was once buried miles deep, rock that bent under pressures that would instantly crush any living thing. The limestone itself remembers this deformation at the molecular level. Crystals reoriented, minerals recrystallized, the internal structure altered by heat and pressure. Yet to the casual observer, it appears simply as stone, as if stone were static, unchanging. McCormick's Creek reveals the truth. Given sufficient time and force, even solid rock flows, bends, transforms under conditions that seem impossible from our human perspective. The White River watershed drains nearly 1/3 of Indiana's total land area, a network of tributaries spreading across the state like the branches of a tree. Every stream, every creek, every river within this vast area ultimately contributes its water to the White River, which flows westward to join the Wabash. This drainage pattern reflects both topography and geological history. The land slopes generally westward, and water follows gravity, seeking the lowest path. But the pattern also reflects glacial influence. The ice sheets diverted pre-existing rivers, created new drainage routes, and left behind deposits that channeled water in particular directions. The White River itself flows through two major forks, the West Fork and East Fork, that converge near Indianapolis. Each fork drains distinct portions of the state, collecting water from thousands of square miles. During heavy rains, the White River can transform from a modest stream to a substantial waterway, its volume increasing tenfold or more as runoff concentrates in its channel. The watershed concept itself offers a useful way of understanding landscape connectivity. Everything that happens upstream affects downstream. A rainstorm in Muncie contributes to the White River's flow near Bloomington. Agricultural runoff from one county appears downstream in another. The river integrates the entire landscape, connecting disparate places through the simple fact of water flowing downhill. Along the shores of Lake Michigan, in sheltered depressions among the sand dunes, grow plants that should not exist this far south. Arctic tundra species, survivors from the last ice age, persist in specific microhabitats called pans, bowl-shaped depressions where conditions replicate those found hundreds of miles north. These pans flood in spring, then dry partially in summer, creating environmental stresses that exclude most plant competitors. The tundra species that colonized this area when glaciers still covered the region found in these pans conditions similar enough to their preferred habitat that they survived as the climate warmed around them. Now, 12,000 years after the glaciers retreated, their descendants continue growing in these isolated pockets, living fossils that represent a direct connection to the Ice Age. The plants themselves are small, unassuming, grasses, sedges, low-growing herbs adapted to cold and moisture stress. They bloom briefly in early summer, produce seed, then enter dormancy. To someone unfamiliar with botany, the pans might appear unremarkable, just wet spots among the dunes. But to those who recognize the species present, these depressions are windows into the past, places where ecology has remained essentially unchanged for millennia, while the surrounding landscape transformed completely. The dunes migrate, forests grow and are cleared, cities rise nearby. Yet in the pans, tundra plants continue their ancient patterns, indifferent to the enormous changes occurring around them. The falls of the Ohio, now largely submerged beneath modern dams and water control structures, once exposed Devonian fossil beds across more than 20 acres of bedrock. When river levels dropped during late summer and autumn, the ancient seafloor emerged from the water, revealing 386 million years of geological time. Coral heads stand frozen in stone, their growth patterns still visible. Brachiopods, shellfish that superficially resemble clams, lie scattered across the bedrock by the thousands, their shells replaced with minerals, but their forms perfectly preserved. Crinoid stems, the segmented stalks of sea lilies, occur in such abundance that some limestone layers consist almost entirely of crinoid fragments. Walking across this fossil bed when exposed, you step on creatures that lived in a warm tropical sea, organisms that predated trees, that existed before insects evolved, that knew a world utterly foreign to anything alive today. The fossils themselves represent only a tiny fraction of the organisms that lived and died here. Preservation requires specific conditions, and most living things decay completely without leaving any trace. Those that do fossilize become incorporated into rock, their organic material replaced molecule by molecule with minerals, creating perfect replicas that can survive hundreds of millions of years. The falls of the Ohio preserve this ancient ecosystem in stone, offering one of the most extensive Devonian fossil beds in North America, a resource for understanding life on Earth during a period when the land was still mostly barren, but the seas teemed with bizarre and beautiful creatures. Beneath Sullivan County, coal seams lie stacked like the pages of a book, each layer representing a distinct ancient forest. The Chinook coal seam is one such layer, part of a vast underground forest that turned to coal over 300 million years. During the Pennsylvanian period, this region supported lush tropical forests growing in coastal swamps. Trees grew, died, and fell into standing water where low oxygen conditions prevented complete decay. Over time, accumulated plant material compressed under the weight of overlying sediment, driving out water and volatile compounds, concentrating the carbon. First it became peat, then lignite, finally bituminous coal, each stage representing increasing pressure and temperature. The coal itself retains traces of its origin: fossil bark impressions, petrified wood, even pollen grains preserved in the carbon matrix. Mining exposes these traces, revealing enormous fossil tree stumps, some standing upright exactly where they grew 300 million years ago, their roots still penetrating the ancient soil. The Pennsylvanian forests existed before dinosaurs, before mammals, before flowering plants. They were dominated by tree ferns, scale trees, and primitive conifers, species that have no modern equivalents. Yet their remains continue to exist as coal, their stored solar energy captured through photosynthesis when the atmosphere contained more carbon dioxide and the climate ran warmer. Now that coal is mined and burned, returning that ancient carbon to the atmosphere, completing a cycle that took hundreds of millions of years. The East Fork of the White River demonstrates what happens when water flows across minimal gradients through easily eroded material. The river meanders so severely that it travels 45 river miles to cover a straight-line distance of just 18 miles. This ratio, river distance to straight-line distance, quantifies the river's sinuosity, its tendency to curve rather than flow directly. Meanders form through a feedback process. Any slight bend in a river channel causes faster flow on the outside of the bend, which erodes the bank more aggressively, which increases the bend, which accelerates the outside flow further. Over time, small irregularities become exaggerated into sweeping curves. The East Fork flows through glacial, till, and alluvial deposits, materials easily eroded, across land so flat that the river has no compelling reason to flow in any particular direction. It wanders across its floodplain, constantly shifting position, abandoning old channels and creating new ones. Aerial photographs reveal its history. Oxbow lakes mark abandoned meanders where the river cut through a narrow neck of land, shortening its course and leaving a crescent-shaped water body behind. The river's floodplain contains evidence of former channels, subtle depressions, and rises that trace paths the river followed decades or centuries ago. This is landscape as process rather than fixed form. The river continuously reshapes its valley, moving soil from one bank to the other, creating topography through its own movement. Given enough time, the East Fork will occupy nearly every position within its floodplain, its meanders migrating like slow waves across the valley floor. Turkey Run State Park preserves box canyons carved through sandstone and shale, narrow gorges that reach 100 feet deep despite being only 10 feet wide at their bases. These canyons formed when massive volumes of glacial meltwater flowed across the landscape, cutting rapidly through rock layers. The water found weaknesses, fractures, joints, bedding planes, and exploited them through erosion, carving downward with the abrasive power of water-carrying sediment. Once initiated, the canyons concentrated flow, which accelerated erosion, which deepened the channels further. The result is a landscape of vertical walls rising from narrow floors, places where sunlight reaches the bottom only at midday, where ferns grow in perpetual dampness, where ice lingers until late spring. The canyon walls reveal the internal structure of the rock. layers of sandstone alternating with shale, each representing different depositional environments in the ancient river delta that existed here 300 million years ago. Some layers contain ripple marks, the fossilized surface of sandbars that existed in that delta. Others show cross-bedding, the internal structure of underwater dunes. Walking through these canyons provides an almost claustrophobic experience, the walls closing in overhead, the sound of water echoing from stone. Yet this narrowness creates its own beauty, the intimate scale, the filtered light, the sense of being inside the earth rather than merely on its surface. The canyons will not last forever. Erosion continues, gradually widening them, and eventually they will become ordinary valleys. But that transformation requires geological time, and for now, they remain narrow and deep, carved by water into forms that seem almost impossible. Buried beneath 150 feet of glacial till lies the channel of the ancient Tees River, a waterway that flowed northwest across Indiana toward the St. Lawrence before the Ice Age. The Tees was a major river system, comparable in size to the modern Ohio, draining much of what is now West Virginia, Ohio, and Indiana. It flowed for millions of years, carving a valley hundreds of feet deep through bedrock. Then the glaciers came. Ice sheets advancing from the north blocked the Tees River's course, forcing the water to find new paths. The river that had flowed for millions of years disappeared, its valley filled with glacial sediment as the ice melted. Today, the buried Tees Channel exists as a subsurface feature, detectable only through drilling and geophysical surveys. Wells drilled into the buried valley encounter thick deposits of sand and gravel, the river's ancient bed and banks, surrounded by finer glacial till. These gravel deposits now serve as aquifers, providing water for towns and farms above. The irony is beautiful. A river killed by glaciation continues to supply water thousands of years after its surface flow ceased. The Tees represents a category of geological feature called a pre-glacial river system, waterways that existed before the Ice Age but were subsequently buried or diverted. Reconstructing their courses requires careful work, analyzing well logs, mapping buried valleys, piecing together a landscape that no longer exists at the surface. Yet understanding these buried rivers is essential for understanding how water moves underground, where aquifers exist, and how the modern landscape came to be. Wesselman Woods in Evansville preserves 200 acres of virgin forest, trees that were already mature when the first European settlers arrived. Some of the oaks and beeches here exceed 400 years in age, their trunks massive, their canopies forming a continuous cover that shades the forest floor. This is old-growth forest, woodland that has never been cleared, never been logged, never been converted to agriculture, and then abandoned. Such forests are extraordinarily rare in Indiana. Less than 1% of the state retains its original forest cover. Most woodland visible today is secondary growth, forests that returned after farming ceased, trees that are decades rather than centuries old. Wesselman Woods escaped clearing largely by accident, its location on low-lying ground near the Ohio River making it less desirable for agriculture. The trees that grow here demonstrate what Indiana's forests looked like before settlement. Diverse species composition with canopy trees, understory species, and ground layer plants arranged in complex relationships developed over centuries. Dead trees stand as snags, providing habitat for cavity-nesting birds and insects. Fallen logs decay slowly on the forest floor, their nutrients gradually released back into the soil. The forest's age creates structural complexity impossible in younger stands, multiple canopy layers, gaps where old trees have fallen, variation in light and moisture that supports diverse plant communities. Walking through Wesselman Woods provides a glimpse of the original landscape, a reminder that forests are not simply collections of trees, but ecosystems that develop character over centuries, acquiring complexity that cannot be replicated through planting or management. Southern Indiana's karst topography contains over 2,500 documented caves, with new passages discovered each year as limestone continues dissolving. Karst is landscape shaped by the dissolution of soluble bedrock, primarily limestone, but also dolomite and gypsum. Water containing dissolved carbon dioxide becomes slightly acidic, capable of dissolving calcium carbonate. Over time, this acidic water percolates through cracks in the limestone, gradually enlarging them into passages, channels, and eventually, caves. The process is self-reinforcing. As passages enlarge, they carry more water, which dissolves more limestone, which enlarges the passages further. The result is an underground landscape as complex as the surface, rivers flowing through darkness, chambers large enough to contain buildings, passages that twist and branch like the tunnels of a vast burrow. Some caves are wet, with active streams flowing through them. Others are dry, abandoned by the water that formed them as the water table dropped or flow diverted to deeper passages. Cave formations, stalactites, stalagmites, flowstone, draperies, grow in dry passages where seeping water deposits dissolved minerals. The caves themselves represent only the voids. The surrounding rock is riddled with smaller passages, fractures, and pores through which water moves. This creates a landscape where surface water can vanish suddenly into sinkholes, where streams disappear underground, where springs emerge from invisible aquifers. The karst continues developing. New sinkholes form when underground voids collapse. Caves grow larger. Water finds new pathways through the rock. It is landscape in constant, slow transformation, shaped by chemistry rather than physical force. Pokagon State Park in northeast Indiana contains Snow Lake, a glacial feature whose waters maintain temperatures cold enough to freeze 30 inches thick even during mild winters. The lake's depth and geological setting create conditions where temperature stratification persists. Cold water, being denser than warm, sinks to the bottom and remains there, insulated from summer heat by the warmer layer above. In winter, when air temperatures drop, the surface freezes quickly because the underlying water is already cold. Ice formation releases latent heat as water transitions from liquid to solid, but this heat dissipates into the cold air rather than warming the water below. As a result, ice thickness accumulates throughout winter, sometimes reaching thicknesses remarkable for Indiana's relatively mild climate. The lake itself formed as a kettle, a depression left when a buried ice block from the retreating glacier finally melted thousands of years ago. Its relatively steep sides and substantial depth create a thermal environment distinct from shallower lakes in the region. Snow Lake's coldness affects its ecology. Fish species present include those adapted to colder water, and aquatic vegetation differs from that found in warmer lakes. The lake's name references the region's heavy lake effect snow, as Pokagon State Park lies close enough to Lake Michigan to receive substantial snowfall when cold air masses move across the lake's relatively warm water, picking up moisture and depositing it downwind as snow. Geography and climate intersect here, creating conditions where a small glacial lake preserves a bit of the Ice Age's lingering influence. The Mississinewa River Valley cuts through deposits that record at least 4 separate glacial advances, each leaving distinct layers visible in road cuts and stream banks. These layers represent different episodes of the Ice Age, periods when glaciers advanced across the region, deposited material, then retreated, only to return thousands of years later. Each glacial advance brought its own sediment load, rock ground from different source areas, till with varying mineral composition, deposits with characteristic color and texture. Between advances, the landscape stabilized. Soils developed in the glacial deposits. Vegetation colonized the barren till. Organic material accumulated. Then the next glacier arrived, bulldozing this soil layer and burying it under fresh till. Today, these buried soils appear as dark layers sandwiched between lighter-colored glacial deposits, marking interglacial periods when the ice retreated and the climate warmed. Geologists study these layers to reconstruct Ice Age chronology: how many advances occurred, how long intervals between them lasted, how far each advance extended. The Mississauga Valley preserves this record because the river has cut through the deposits, exposing their internal structure. The glacial layers lie stacked like pages in a book, each representing a chapter in the region's climatic history. Reading them requires careful observation, identifying till from outwash, recognizing buried soils, mapping how layers correlate from one exposure to another. But the effort reveals deep time made visible, tens of thousands of years compressed into vertical sequences measured in feet. Squire Boone Caverns, named for the explorer who allegedly sheltered there in 1790, contains an underground waterfall that drops 30 feet through a limestone chamber. The waterfall exists because underground streams, like surface rivers, flow downhill, following gradients through cave passages. Where a passage encounters a vertical shaft or a sudden drop in floor level, the water must descend, creating a waterfall. The falling water carries tremendous erosive power despite its underground location. The constant impact gradually deepens the plunge pool, sometimes undermining the rock lip over which the water falls, slowly moving the waterfall upstream as sections collapse. The sound of falling water in the cave amplifies and echoes from stone walls, creating acoustic effects impossible on the surface where sound disperses into open air. The waterfall chamber itself displays the beauty possible in underground spaces: flowstone where minerals have deposited on walls and floors, stalactites hanging from the ceiling, the water itself appearing almost black in the beam of artificial lights, its true color visible only where turbulence creates white water. Squire Boone, if he truly sheltered here while fleeing pursuing Native Americans, would have experienced absolute darkness, relieved only by whatever torch or fire he could maintain. The cave would have provided protection, but also profound disorientation. No day or night, no stars to navigate by, only stone and water and darkness extending in all directions. Today, the caverns are illuminated for visitors, pathways installed, safety ensured. But turn off the lights, and the cave returns to its natural state, a darkness so complete it seems almost tangible. The Iroquois moraine stretches across northern Indiana like a gentle wave frozen in soil and stone, a ridge of glacial debris 200 feet high, marking where the ice sheet paused for centuries. Moraines form at glacier margins, where advancing ice meets melting at equilibrium. The glacier continues moving forward, but its edge remains stationary, because ice arrives at the same rate it melts. During this pause, the glacier acts as a conveyor belt, constantly delivering sediment to its margin. Rock, soil, boulders, everything trapped in the ice accumulates at the edge, building a ridge that grows higher the longer the glacier remains stationary. The Iroquois moraine represents one such pause, a period lasting perhaps hundreds of years when the ice sheet's advance stalled. When the glacier finally retreated, the moraine remained as a permanent landscape feature, a ridge marking the ice's temporary boundary. Today, The moraine influences drainage patterns. Streams originate on its slopes, flowing either north toward the Great Lakes watershed or south toward the Wabash system. Roads follow the moraine's crest in places, taking advantage of the high ground. The ridge itself remains visible in the landscape, a subtle but persistent topographic feature shaped by ice that melted 12,000 years ago. Its influence continuing long after the ice itself has vanished completely. The Salamone River cuts through layers of Silurian dolomite that contain fossils from shallow seas covering Indiana 425 million years ago. Dolomite is limestone that has undergone chemical alteration, its calcium carbonate partially replaced by magnesium through the action of mineral-rich groundwater. The process transforms the rock's properties, making it slightly harder and more resistant to weathering than ordinary limestone. But the fossils within remain, brachiopods primarily, those peculiar shellfish that dominated Paleozoic seas. Brachiopods superficially resemble clams, with two shells protecting the soft body within, but their internal anatomy differs completely. They filtered nutrients from seawater, their shells opening slightly to allow water flow across specialized organs. When the organisms died, their shells accumulated on the seafloor, sometimes in such abundance that entire rock layers consist almost entirely of brachiopod fossils. The Salamone River, in carving its valley, has exposed these ancient seafloor deposits, bringing them back into the light after hundreds of millions of years of burial. The fossils themselves appear as impressions in the rock, or sometimes as actual shell material, replaced molecule by molecule with different minerals. Touch them, and you contact the shape of life from an era when the land was barren, when no trees existed, when the most complex terrestrial organisms were primitive arthropods venturing onto shores between tides. The river continues cutting, continues exposing deeper and older layers, gradually working its way down through geological time. Beneath the migrating dunes at Indiana Dunes National Park, ancient black oak savannas lie buried under 80 feet of wind-blown sand. These savannas existed here thousands of years ago, when the post-glacial climate was drier and fires swept regularly across the landscape. Black oak grows in open, fire-maintained ecosystems where frequent low-intensity burns prevent the establishment of more shade-tolerant species. The savannas would have appeared park-like, scattered large oaks with grassy understory, quite different from closed canopy forest. Then conditions changed. Perhaps the climate became wetter, reducing fire frequency. Perhaps lake levels dropped, exposing more beach sand to wind erosion. Whatever the cause, sand began accumulating, slowly burying the savanna beneath advancing dunes. The trees died as sand covered their trunks, suffocating root systems, but the wood remained preserved in the anaerobic environment under the dunes. Occasionally, erosion exposes these buried forests. A storm strips away sand, revealing blackened logs, sometimes entire tree trunks lying horizontal or leaning at angles, monuments to a landscape that existed millennia ago. The wood is often remarkably preserved, still identifiable as oak, still showing growth rings that recorded the climate conditions of its time. Then the dunes migrate further, or new sand accumulates, and the ancient forest disappears again beneath layers of quartz grains. It is geography as palimpsest, landscapes written over previous landscapes, each era leaving traces that future erosion might expose. Spring Mill State Park contains a functioning grist mill powered by water from a natural spring that produces 9,000 gallons per minute. 9,000 gallons per minute is an extraordinary discharge rate, a volume substantial enough to turn mill wheels, to power machinery, to serve entire communities. The spring emerges from limestone bedrock, fed by an underground aquifer whose recharge area and full extent remain unknown. The water appears at a constant temperature year-round, cool even in summer heat, its clarity remarkable. The spring has flowed at least as long as historical records document, and geological evidence suggests it has been flowing for thousands of years, possibly since the landscape stabilized after the glaciers retreated. The mill that stands here now is a reconstruction, but mills have operated at this site since the early 19th century, harnessing the spring's reliable flow. The water's constancy made it valuable. Unlike surface streams that flood and dry with seasons, the spring maintained steady output regardless of weather. This reliability reflects the aquifer's size and the buffering effect of groundwater storage. Rainfall that falls today might not emerge from the spring for months or even years, having percolated through soil and rock, moving slowly through interconnected pores and fractures, joining an underground reservoir whose residence time is measured in decades. The spring integrates rainfall across time, smoothing out the variations between wet and dry periods, creating flow that appears unchanging despite the variable climate above. In Crawford County, Wyandotte Cave extends over 9 miles through limestone bedrock, its passages connecting chambers large enough to hold entire buildings. The cave is among Indiana's most extensive, its mapped length representing only the explored sections. Additional passages almost certainly exist in areas too dangerous or too restricted to access. One chamber, called Monument Mountain, rises 135 feet inside a single room, a space so vast that early explorers could barely believe it existed underground. The mountain is not actually a mountain, but rather a massive pile of breakdown. Rock that has fallen from the ceiling over thousands of years, accumulating on the cave floor until it formed a hill within the chamber. Climbing Monument Mountain in absolute darkness, with only primitive lighting, must have been a surreal experience for 19th century explorers. Today, the cave offers tours through developed sections, but much of Wyandotte remains wild cave, accessible only to experienced spelunkers. The passages wind through multiple levels, some following underground streams, others dry and decorated with formations. The cave's formation required millions of years of water-dissolving limestone, enlarging fractures into passages, gradually creating the three-dimensional maze that exists today. And the process continues. Water still seeps through the rock, still dissolves calcium carbonate, still deposits minerals as flowstone and stalactites. The cave is not a static museum, but an active geological process, slowly changing, slowly growing, expanding into the surrounding bedrock grain by grain. The ancient coral reef that became Salem limestone underlies most of south-central Indiana, the same stone used to construct the Empire State Building, the Pentagon, and countless other significant structures across America. This limestone formed 340 million years ago during the Mississippian period, when Indiana lay beneath a warm, shallow sea comparable to the modern Bahamas. Coral reefs grew in these clear waters, their polyps extracting calcium carbonate from seawater to build protective skeletons. The reefs themselves would have resembled modern coral reefs in structure, if not in species, complex three-dimensional frameworks, providing habitat for diverse marine life. When the sea withdrew and the reef died, burial and lithification transformed the organic structure into solid rock. The resulting limestone possesses unusual properties. It is relatively soft when first quarried, easy to cut and shape, but hardens when exposed to air, making it ideal for construction. The stone's color is consistent, a light gray or buff tone that weathers well. Its texture is fine-grained, uniform, free of the flaws that make some stone difficult to work. These qualities made Salem limestone one of the most sought-after building stones in America during the late 19th and early 20th centuries. Quarries around Bedford, Bloomington, and other south-central towns shipped trainloads of stone to construction projects nationwide. The stone's origin as a coral reef is still visible in polished sections. Fossil coral, crinoid stems, brachiopod shells appear as darker inclusions in the lighter matrix. A building faced with Salem limestone is essentially clad in ancient seafloor, its walls containing fossils 340 million years old. Lake Monroe covers 10,750 acres in south-central Indiana, making it the state's largest lake. But the qualifier is important. Lake Monroe is entirely artificial, created in 1965 when engineers dammed Salt Creek. Before the dam, Salt Creek flowed through a valley carved over thousands of years. The creek meandered across its floodplain, draining a substantial watershed in the hilly terrain of south-central Indiana. Then the dam went up, the valley flooded, and the lake formed. Today, Lake Monroe provides flood control, water supply, and recreation, but it remains a human creation, dependent on the dam for its existence. Remove the dam, and the lake would drain within days. Salt Creek would resume flowing through its original valley, and the landscape would return to something approximating its pre-dam state. The lake bottom preserves evidence of what existed before flooding: old roads, foundations, fence lines, trees that were killed when water rose over their root systems. Occasionally, during drought, when lake levels drop substantially, these artifacts emerge from the water, momentarily visible before the lake refills. The artificial nature of Lake Monroe distinguishes it from natural glacial lakes in northern Indiana, which formed through geological processes without human intervention. Those lakes exist because ice created depressions that filled with water. Lake Monroe exists because humans built a dam. Both contain water, both support similar ecosystems, but their origins and permanence differ fundamentally. Twin Swamps Nature Preserve in Posey County contains bald cypress trees growing in standing water, their trunks flared at the base, their distinctive knees, woody projections from root systems, rising above the water's surface. These are trees associated with the Deep South, with Louisiana bayous and Florida swamps, species that seem profoundly out of place in Indiana. Yet here they grow, thriving in conditions that replicate their preferred habitat despite the latitude. The preserve occupies the southwestern corner of Indiana, a region that escaped glaciation and maintains slightly warmer, wetter conditions than areas farther north. But climate alone doesn't explain the cypress. Their presence here represents a biogeographic relict, a population that once occupied a much larger range during warmer post-glacial periods, then became isolated as climate cooled and their range contracted southward. Most cypress populations in the Midwest disappeared, but a few persisted in protected sites where local conditions permitted survival. Twin Swamps is one such refugium, a place where southern ecology hangs on at the edge of its range. The trees themselves demonstrate remarkable adaptation. They survive Indiana winters that would seem too harsh for subtropical species, entering dormancy when cold arrives, resuming growth when temperatures warm. Their wood is rot-resistant, capable of standing in water for centuries without decay. Some of the cypress at Twin Swamps are quite old, perhaps several hundred years, their presence a living connection to the warmer climates that once extended farther north. Beneath the coal fields of southwestern Indiana, fossil tree stumps stand upright in ancient mud, preserved exactly where they grew 300 million years ago. These are not fallen trees that somehow came to rest vertically, but actual rooted stumps, their bases still penetrating the soil layer that supported them in the Pennsylvanian period. The preservation occurred because the forest floor was flooded. Water rose rapidly enough to kill the trees, but gently enough to leave them standing. Sediment then buried the stumps, sealing them away from oxygen and decay. Over geological time, minerals replaced the wood cells, creating stone replicas that retain the original structure in perfect detail. Mining operations occasionally expose these fossil forests, cutting through coal seams to reveal the upright stumps in the overlying rock. The experience of seeing them is uncanny. Trees that were alive when the continents occupied different positions, when the climate ran hot and humid, when the atmosphere contained oxygen levels substantially higher than today. The stumps themselves appear gray or brown, their bark texture still visible, sometimes with root systems spreading into the fossilized soil beneath. They stand as monuments to the immensity of geological time, to the fact that landscapes we think of as permanent are actually transient, that forests can become coal, that stone remembers organic life even after hundreds of millions of years have erased every other trace. The Mississinewa Reservoir flooded a river valley that once drained directly to the Wabash through a channel carved during glacial retreat. Before the reservoir existed, the Mississinewa River flowed through this valley in its natural state, meandering across its floodplain, rising during spring floods, dropping during summer droughts. The valley itself reflected thousands of years of the river's work. Sediment deposited during floods had built a flat floodplain. The river had carved meanders through the valley floor. Vegetation had established along the banks. Then, in 1968, engineers completed the Mississinewa Dam, and water backed up behind it, flooding the valley. Farms, roads, bridges, even entire small communities disappeared beneath the rising water. Today, the reservoir provides flood control for communities downstream, prevents the kind of devastating floods that historically plagued the Wabash Valley. But the cost was the loss of the natural river valley, its transformation into a reservoir whose level fluctuates based on management decisions rather than natural hydrology. The shoreline shows evidence of this artificial regime. Vegetation struggles to establish because water levels change too frequently, exposing and flooding the shore zone on schedules that don't match plant life cycles. During drawdowns, when the reservoir level drops substantially, the old valley becomes partially visible again. Creek channels that fed the Mississinewa, remnants of the original floodplain, suggestions of the landscape that existed before the flood. Hemmer Woods contains virgin forest where beech trees with trunks 6 feet in diameter grow alongside sugar maples that were saplings when European settlers first arrived. 6 feet in diameter represents extraordinary age for a beech, likely 300 to 400 years, perhaps longer. Trees this size are rare in Indiana, where most forest has been cleared at least once. Hemmer Woods survived because of its location, its topography, its sheer luck in escaping the axes and saws that removed most of Indiana's original forest cover. Walking through the preserve, you experience forest structure impossible in younger stands. The canopy is tall and complete, formed by trees that have won the competition for light over centuries. Below the canopy, shade-tolerant species form an understory layer. The ground itself is covered with spring ephemeral wildflowers, species that complete their growth cycle before the canopy trees leaf out and shade the forest floor. Dead trees stand as snags, their trunks riddled with woodpecker holes, their bark sloughing off in sheets. Fallen logs in various stages of decay lie scattered across the ground, their wood softening as fungi and insects break down the cellulose. The soil is deep and rich, built up over centuries from decomposing leaves and wood. This is old-growth forest structure, complex, layered, developed over timescales that exceed human planning horizons. It represents what most of Indiana looked like before settlement, when vast forests stretched across much of the state, broken only by prairies in the northwest and river valleys where flooding prevented tree establishment. The limestone bedrock beneath Bloomington dissolves at a rate of approximately 1 inch every 1,000 years, a process that creates new sinkholes and caves continuously. 1 inch per 1,000 years seems impossibly slow, yet it accumulates. Over 10,000 years, 10 inches of limestone disappears. Over 1,000,000 years, 80 feet. The dissolution occurs through the action of slightly acidic water, rainwater that has absorbed carbon dioxide from the atmosphere, and soil becomes weak carbonic acid, capable of dissolving calcium carbonate. The water percolates through fractures in the limestone, slowly enlarging them through chemical erosion. Where water concentrates along particular pathways, dissolution accelerates, creating underground channels that eventually become caves. At the surface, dissolution sometimes creates sinkholes, depressions that form when underground voids collapse or when overlying soil gradually subsides into dissolving bedrock. Bloomington and surrounding areas experience periodic sinkhole formation, sometimes discovering new depressions in backyards or beneath roads. The process is generally slow and predictable enough to manage, but occasionally a sinkhole opens suddenly, swallowing whatever sits above it. The limestone's solubility creates infrastructure challenges. Building foundations must account for the possibility of underground voids. Roads sometimes require repair when subsurface collapse creates potholes or larger failures. Yet this same solubility also creates the region's spectacular caves, its springs, its karst landscapes. The dissolution is both problem and treasure, evidence that bedrock is not permanent, that even stone yields to water given sufficient time. In Pike County, the Patoka River bottomlands flood annually, each flood depositing fresh layers of silt that have built fertile soils over thousands of years. River flooding is often portrayed as disaster, but it represents the river's natural function, spreading sediment across its floodplain, renewing soil fertility, creating habitat for species adapted to periodic inundation. The Patoka follows this ancient pattern. During spring, when snow melts and rain accumulates faster than the river can discharge it, water overtops the banks and spreads across the floodplain. The velocity slows once water leaves the main channel, and this slower water drops its sediment load, the sand and silt the river has been carrying. Each flood adds a thin layer, perhaps only millimeters thick, but the layers accumulate over decades, over centuries, over thousands of years. These flood deposits build deep, rich soils. The bottomland forests that grow here are adapted to flooding. Species like silver maple, cottonwood, and sycamore tolerate having their roots submerged for weeks at a time. These forests provide habitat for wildlife, filter runoff before it reaches the main channel, and store floodwater that would otherwise threaten downstream communities. The Patoka's bottomlands represent river ecology, functioning as it evolved to function, without levees or channelization constraining the water. The floods may inconvenience humans who've built in the floodplain, but to the river and the ecosystem it supports, flooding is essential process, not catastrophe. 18,000 years ago, the Michigan lobe of the Laurentide ice sheet reached its maximum extent across northern Indiana, ice piled 2 miles high. 2 miles of ice represents almost incomprehensible weight pressing down on the landscape, millions of tons per square mile, enough to deform the Earth's crust, depressing it hundreds of feet under the load. The ice itself consisted of snow that had accumulated over thousands of years in Canada, compacting under its own weight until it transformed from snow to glacial ice. The ice sheet wasn't stationary, but flowed like extremely slow liquid, moving outward from centers of accumulation, creeping southward at rates measured in feet per year. At its maximum extent, the Michigan lobe covered all of northern Indiana and part of central Indiana before warmer climate halted its advance. The ice's erosive power was immense. It ground bedrock to powder, plucked boulders and carried them hundreds of miles, obliterated pre-existing topography. Beneath the ice, the landscape endured perpetual winter, temperatures far below freezing, no sunlight, enormous pressure. Then climate warmed. The ice began melting, and over several thousand years, the glacier retreated back across the region, leaving behind the till, moraines, and outwash deposits that shape modern Indiana. The ice's retreat was not smooth. It advanced and retreated multiple times, pausing at particular positions long enough to build substantial moraines. Eventually, around 12,000 years ago, the ice withdrew from Indiana completely, revealing a landscape transformed, scraped raw, ready for recolonization by plants and animals moving north behind the retreating ice. Cedar Bluff Nature Preserve contains western red cedar, growing on limestone cliffs far from the species' normal range, survivors of cooler climates that existed after the Ice Age. Western red cedar typically grows in the northwestern United States, preferring cool, moist conditions and well-drained soils. Its presence in southern Indiana represents another biogeographic anomaly, a relict population that colonized this area during the late glacial period when Indiana's climate was cooler than present. The cedars at Cedar Bluff survive because the cliffs create a microclimate. North-facing slopes remain cool even in summer. Limestone rock maintains moisture, and elevation provides drainage. These conditions approximate the cedar's preferred habitat despite the difference in latitude. As climate warmed over the past 10,000 years, most cedar populations in the Midwest died out, unable to tolerate the warmer, drier conditions. But a few populations persisted in protected sites where local topography buffered them from regional climate change. Cedar Bluff is one such site, a place where geography creates conditions cool enough and moist enough for the cedars to survive. The trees themselves are not large. The harsh growing conditions and marginal habitat limit their size, but their presence is significant. They represent direct connections to the late glacial landscape, to the cool forests that covered much of the Midwest when mammoths still roamed the plains. Their persistence demonstrates how local topography can create refugia where species survive outside their normal range. The Eel River meanders through glacial outwash plains in Miami County, its modern course following paths of least resistance through ancient gravel deposits. Glacial outwash consists of sediment deposited by meltwater streams flowing from the glacier's margin. Unlike till, which is unsorted material dumped directly by ice, outwash is sorted by water flow. Coarser gravel and sand near the glacier where water flows fast, finer sand and silt farther away where velocity decreases. These outwash deposits can be hundreds of feet thick, filling valleys that existed before glaciation. The Eel River inherited a landscape sculpted by these processes: broad, flat plains of outwash, subtle topography, channels already established by glacial meltwater. The river flows through this material, easily eroding the sand and gravel, constantly shifting its course within the outwash plain. Historical maps show the eel in different positions, its meanders migrating across the valley, channels abandoned and new ones created. This mobility is characteristic of rivers flowing through easily eroded material. There's little to constrain their course, so they wander freely, responding to floods and local variations in sediment supply. The outwash itself serves as an aquifer, its porous gravel and sand transmitting groundwater efficiently. Wells drilled into outwash deposits typically yield abundant water, tapping into the same pore spaces that once carried glacial meltwater. The Eel River is essentially flowing through the remnants of that ancient drainage system, following paths first established when ice still covered regions to the north. Beneath downtown Indianapolis, limestone bedrock contains solution cavities large enough to collapse roads, requiring constant geological monitoring to prevent infrastructure failure. Solution cavities form through the same process that creates caves. Acidic groundwater dissolves limestone, creating voids in the bedrock. In rural areas, such cavities might collapse to form sinkholes, noticed only if they're particularly large. But in urban areas, even small collapses can cause significant problems. A void forms in the limestone, perhaps 20 or 30 feet below the surface. Soil gradually subsides into the void, creating a depression at the surface. If the void is directly beneath a road, the pavement may initially show only slight sagging, but eventually the unsupported material collapses, creating a crater that can swallow vehicles. Indianapolis, built partly on karst topography, must continually monitor for such features. Ground-penetrating radar can detect some voids before they collapse. Boreholes can probe suspected areas. When voids are discovered, they're typically filled with concrete or grout to prevent collapse. But new voids form constantly. The limestone continues dissolving wherever water flows through it. The city exists atop bedrock that is slowly, imperceptibly hollowing out beneath it. A landscape in gradual transformation. Most residents never think about the limestone beneath their feet, never consider that solid ground is actually riddled with fractures and voids, some empty, some water-filled, some gradually enlarging toward eventual collapse. The rock remembers that it was once seafloor sediment, and water continues the work of returning it to that dissolved state. The Buffalo Trace, a prehistoric bison migration route across southern Indiana, wore grooves in solid limestone that remain visible 10,000 years later. Bison migrated seasonally, following traditional routes between summer and winter ranges. Their movements were not random wandering, but purposeful travel along specific paths, routes learned and transmitted across generations. In areas where these routes crossed exposed bedrock, thousands of bison walking the same path year after year, century after century, wore depressions into the stone. The phenomenon seems almost impossible. How can soft hooves wear solid rock? But consider the time involved, the numbers. If 1,000 bison cross a particular spot annually for 10,000 years, that's 10 million passages. Each hoof strike removes microscopic amounts of rock, but the passages accumulate. The limestone at the Buffalo Trace shows the result, grooves several inches deep, following the old migration route. The trace itself extends for miles, a pathway connecting the Ohio River Valley with interior regions. Native Americans recognized and used these traces, understanding that bison had found the easiest routes through difficult terrain. Later, European settlers also used them, and some modern roads follow portions of the ancient trace. The grooves themselves are gradually eroding away. 10,000 years of weathering since the bison disappeared has begun to soften the depressions. Eventually, rain and frost will erase them completely, but for now, they remain as evidence of the bison herds that once moved across this landscape in numbers large enough to wear stone through the simple repetition of their passing. At Hanging Rock in Crawford County, Massive sandstone overhangs project 50 feet beyond their supporting cliffs, structures that seem to defy gravity, yet have stood for thousands of years. These overhangs form through differential erosion. The sandstone is not uniform, but consists of layers with varying resistance to weathering. Some layers are well cemented, their sand grains tightly bound together. Others are more friable, their cement weaker. Rain, freeze-thaw cycles, and chemical weathering attack the weaker layers more aggressively, removing material and creating undercut profiles. The harder layers above resist erosion and remain projecting outward, creating overhangs that extend far beyond the cliff face below. Eventually, these overhangs will collapse. Gravity ensures it. But the timing is unpredictable. Some overhangs have stood for millennia and show no signs of imminent failure. Others collapse suddenly, sometimes triggered by frost, sometimes by earthquakes, sometimes by the simple cumulative effect of weathering reducing the overhang's support until it can no longer bear its own weight. Native Americans used these rock shelters for temporary camps, taking advantage of the protection from weather. The overhangs provide dry areas even during heavy rain, and the south-facing exposures collect solar heat in winter. Today, the overhangs attract climbers, hikers, and geologists who study the processes creating these precarious structures. Stand beneath hanging rock, and you exist in a kind of suspended moment. The overhang has stood for ages and might stand for ages more, or it might collapse tomorrow. The stone gives no indication which future awaits. The Driftwood River earned its name from massive log jams that once blocked its course for miles, accumulations of trees swept from banks during spring floods and trapped where the channel narrowed or curved sharply. These jams were not simple collections of a few logs, but vast tangles of timber. Hundreds of trees interlocked, creating dams that backed water upstream and forced the river to seek alternate routes around the obstruction. The wood came from bank erosion during floods, when entire trees toppled into the current, their root systems unable to hold against the force of moving water undercutting the soil. Once in the river, trees floated downstream until they lodged against obstacles, rocks, tight bends, other logs. Subsequent floods brought more trees, building the jam larger. Some jams persisted for years, even decades, becoming semi-permanent features that influenced the river's hydrology. Settlers encountered these obstructions when attempting to navigate the river, finding passage blocked by timber barriers that required considerable effort to clear. Eventually, most major log jams were removed to improve navigation and drainage. But the river's name remains as testament to a time when woody debris was abundant, when forests grew close to riverbanks, when floods regularly recruited trees into the channel. Today, the driftwood flows relatively clear of such obstructions, its banks often cleared for agriculture, its log jams relegated to historical accounts, and the name that persists on maps. In the Indiana dunes, ecological succession compresses into visible distance, progressing from bare beach to climax forest in less than a mile. Stand at the lakeshore and you see sand, beach environment, plants sparse or absent, conditions harsh with wind, salt spray, temperature extremes. Walk inland and pioneer species appear, grasses and herbs adapted to mobile sand, species whose roots can follow as dunes shift. Farther inland, shrubs establish where dunes have stabilized, their roots binding the sand, their shade and leaf litter beginning to modify conditions. Continue walking, and you encounter young forest, cottonwood and willow, fast-growing trees that tolerate sandy soils and harsh conditions. Finally, a quarter mile or less from the beach, you reach mature forest, oak, beech, maple, a fully developed woodland ecosystem with deep soil, diverse understory, structural complexity that took centuries to develop. This progression, which normally occurs over thousands of years as landscape changes, here exists simultaneously in space because the dunes themselves are arranged in age sequence. The beach is newest, sand freshly deposited. The dunes immediately inland are decades old. The forest beyond grows on dunes that stabilized centuries ago. Walk from water to forest, and you walk through time, witnessing succession as a spatial pattern rather than temporal process. The entire sequence demonstrates how life colonizes bare mineral substrate, how organisms modify conditions, making them more suitable for other species, how complexity builds through stages from simple to intricate. The ancient Cincinnati Arch, a geological uplift beneath eastern Indiana, prevented complete glacial coverage and created the unglaciated pocket of south-central Indiana. The arch is not a visible landscape feature, but a subsurface structure, a broad upwarp in the bedrock extending across multiple states. Its formation occurred hundreds of millions of years ago through tectonic forces that gently warped horizontal rock layers into a dome. The uplift raised the land surface slightly, not dramatically. We're discussing perhaps a few hundred feet of elevation difference spread across hundreds of miles. But this subtle uplift influenced the glaciers profoundly. Ice flows downhill following gravity, taking paths of least resistance. The Cincinnati Arch represented higher ground, a subtle topographic barrier that divided ice flow. The Michigan Lobe flowed along the arch's western flank. The Erie Lobe followed the eastern side, but the crest remained ice-free, a peninsula of unglaciated terrain surrounded by ice sheets thousands of feet thick. This accident of geology preserved landscapes that would otherwise have been erased by glaciation. The hills of south-central Indiana, the caves, the karst topography, all exist because the Cincinnati Arch deflected the ice. Had the arch not existed, glaciers would have covered the region, grinding away the hills, filling the valleys, creating the same flat till plains that characterize northern Indiana. Instead, this area retains its pre-glacial character, its bedrock-controlled topography, its ancient valleys carved by rivers that predate the Ice Age. At Donaldson Cave, an underground stream flows year-round at exactly 54 degrees Fahrenheit, fed by an aquifer that averages rainfall over decades. 54 degrees represents the mean annual temperature deep underground, the point at which seasonal variations cease to penetrate. Surface temperatures swing wildly, freezing in winter, hot in summer. But these fluctuations diminish with depth. A few feet underground, temperature variation decreases. 10 feet down, it becomes minimal. 50 feet down, temperature remains essentially constant regardless of season. The water flowing through Donaldson Cave originates as rainfall that infiltrated the soil, percolated through rock, and joined the groundwater system. The water that emerges today might have fallen as rain months or years ago, having spent that time moving slowly through aquifer pores and fractures. This long residence time allows the water to equilibrate with bedrock temperature, arriving at the cave at 54 degrees, whether the surface air is 0 or 90. The constancy creates a unique environment. Cave organisms never experience temperature variation. Cave formations grow at steady rates. Ice never forms inside. The stream itself carves gradually deeper into the cave floor, lowering its channel by microscopic amounts annually, enlarging passages through the patient work of erosion. In winter, when surface streams freeze solid, Donaldson Cave continues flowing unchanged. Its temperature adequate to prevent freezing, its source protected deep underground where winter never reaches. The The Kankakee Outwash Plain in northwest Indiana consists of sand and gravel deposits 200 feet deep in places, sediment sorted by size as glacial meltwater slowed across the landscape. Outwash forms when meltwater streams flow from a glacier's margin, carrying heavy loads of sediment. Near the ice, where water flows fast and turbulent, it can carry even large cobbles. As the stream spreads across the plain beyond the glacier's edge, velocity decreases, and the water drops its load according to size. Coarsest material first, finest last. The result is sorted deposits with the largest particles near the ice margin, progressively finer material farther away. These deposits accumulated over thousands of years during the glacier's retreat, each summer's melt season adding new layers. The Kankakee Outwash Plain preserves this history in vertical sequences 200 feet thick, layer upon layer of sand and gravel, each representing a distinct meltwater event, collectively recording the glacier's slow withdrawal northward. Today, the Outwash Plain appears as exceptionally flat terrain with sandy soils and rapid drainage. Rain that falls on the plain infiltrates immediately into the porous deposits rather than running off across the surface. This makes the region prone to drought, but also creates valuable aquifers. The same porosity that allows rapid infiltration also transmits groundwater efficiently. Wells drilled into the outwash can yield enormous quantities of water, tapping into sand and gravel deposited by glacial meltwater thousands of years ago. Water stored in pore spaces that once carried floods from melting ice. In the Hoosier Prairie Nature Preserve, tallgrass prairie remnants contain plant species that once covered 15% of Indiana before agricultural conversion. Tallgrass prairie is an ecosystem dominated by grasses that can reach 8 feet high by late summer, their roots penetrating equally deep into the soil. These prairies once stretched across northwestern Indiana and into Illinois, vast grasslands maintained by periodic fire that prevented tree encroachment. The grasses themselves are adapted to fire. Their growing points lie below ground, protected from flames, and they resprout vigorously after burning. Trees, by contrast, are killed by frequent fire, unable to establish in prairies where burning occurs every few years. Before European settlement, these fires occurred naturally, started by lightning or deliberately set by Native Americans who understood that burning maintained productive hunting grounds. When settlement brought fire suppression and agricultural conversion, most prairie disappeared, plowed under for crops, or, when protected from fire, succeeded to woodland. Today, less than 1% of Indiana's original prairie remains, preserved in small fragments like Hoosier Prairie. These remnants contain incredible plant diversity, dozens of grass species, hundreds of forbs, each adapted to specific moisture and light conditions within the prairie mosaic. In spring, prairie wildflowers bloom in waves, pasque flowers, then shooting stars, then prairie smoke. By summer, the grasses dominate, their seed heads rippling in wind like waves on water. The prairie requires active management, controlled burns replicating natural fire, without which it would quickly succeed to shrubland and eventually forest. The limestone beneath Mitchell contains oolitic grains that formed as calcium carbonate precipitated around sand grains in warm Mississippian seas. Oolitic limestone has a distinctive texture, appearing almost like fish eggs when viewed closely. Small spherical grains packed together, each grain consisting of concentric layers wrapped around a central nucleus. These ooids form in shallow, agitated seawater where calcium carbonate is supersaturated. As waves roll sand grains across the seafloor, calcium carbonate precipitates on their surfaces, coating them with thin layers. The grains roll back and forth with each wave, accumulating additional layers, growing larger. The process requires specific conditions: warm water, high salinity, constant agitation, abundant calcium carbonate. The Mississippian Sea that covered Indiana provided these conditions, its shallow waters clear and tropical, its floor accumulating oids by the cubic mile. Eventually, these deposits lithified, the oids cementing together into solid limestone. The rock that resulted is prized for construction. It's relatively uniform in texture, saws easily when fresh from the quarry, hardens upon exposure to air. Much of the Salem limestone quarried near Mitchell consists of oolitic zones, layers where oids dominate the rock composition. Touch this stone and you feel spheres formed in warm seawater 340 million years ago, each grain a tiny record of waves rolling across a seafloor that became Indiana. At Hemlock Cliffs, box canyons shelter eastern hemlock trees at the westernmost edge of their natural range, clinging to cool microclimates in deep shade. Eastern hemlock typically grows in the Appalachian Mountains and regions farther east, preferring cool, moist conditions and acidic soils. Its presence in southern Indiana represents a range extension, a population existing far from the species' core distribution. The hemlocks survive here because the canyons create conditions cooler and wetter than the surrounding landscape. The canyon walls block direct sunlight for most of the day, maintaining shade even in summer. Seepage from the canyon walls provides constant moisture. Cold air settles into the canyon bottom at night, creating temperatures several degrees cooler than the plateau above. These factors combine to create a microclimate similar to regions hundreds of miles northeast. The hemlocks growing here are not large. The marginal conditions limit their growth, but their presence is ecologically significant. They represent a relict population, descended from trees that colonized the area during cooler post-glacial periods. As climate warmed, most hemlocks in the Midwest died out, unable to tolerate the heat and drought. But in protected sites like Hemlock Cliffs, they persisted, sheltered by topography from regional climate change. The canyons themselves are beautiful independent of the trees. Narrow gorges with vertical sandstone walls, waterfalls dropping over ledges, ferns growing from cracks in the rock. The hemlocks add an additional layer of interest, living connections to different climatic conditions, survivors clinging to habitats where accidents of geology replicate the climate of distant regions. The Maumee Torrent, a catastrophic glacial lake outburst 14,000 years ago, carved the Wabash Valley in a matter of days. During the glacier's retreat, meltwater accumulated in vast lakes dammed by ice. These glacial lakes were enormous, some larger than the current Great Lakes, held in place by ice barriers. Glacial Lake Maumee occupied the Lake Erie Basin and surrounding lowlands, its water levels rising as meltwater accumulated faster than drainage could remove it. Eventually, the ice dam containing the lake failed. Whether through floating, melting, or catastrophic breach is uncertain. When it failed, the lake drained in an event of almost unimaginable violence. Water that had accumulated over years or decades released in days or even hours, a flood carrying enormous volumes at tremendous velocity. This torrent flowed southwest across Indiana, following the lowest path available, scouring the landscape as it went. The Wabash Valley shows evidence of this event: oversized valleys, channels too large for the modern river to have carved them, deposits of coarse gravel far from any current stream. The flood's power was sufficient to move boulders weighing tons, to strip soil down to bedrock, to carve channels hundreds of feet wide. Then it was over. The lake drained, the flow ceased, and the landscape stabilized again. The Wabash River inherited this oversized valley, flowing through a channel carved by forces it could never generate itself. a reminder that landscapes sometimes change not gradually, but catastrophically. In Orange County, Wesley Chapel Gulf swallows Lick Creek into an underground passage that doesn't re-emerge for 3 miles. A gulf, in karst terminology, is a blind valley, a valley that ends not at a confluence with another stream, but at a sinking point where water disappears underground. Wesley Chapel Gulf demonstrates this phenomenon dramatically. Lick Creek flows above ground like any normal stream, carrying water from its watershed toward eventual junction with larger waterways. Then it reaches the Gulf, and the creek simply ends. The water flows into a swallow hole, a depression in the stream bed where dissolution has created an opening into underground channels. All the creek's flow, in dry periods perhaps a few gallons per second, in flood conditions much more, vanishes into this opening. The water doesn't cease flowing. It continues underground, following limestone channels carved by the same dissolution processes that created the swallow hole. For 3 miles, the creek flows in darkness through passages humans have not fully explored. Then it re-emerges at a spring, daylight again, resuming its surface course. The creek has been flowing this way for thousands of years, possibly longer, its course divided between surface and subsurface sections. During exceptional floods, when the underground passages can't accommodate the volume, water backs up in the Gulf, creating a temporary lake that drains once the flood subsides. The phenomenon reminds us that the surface landscape represents only part of the hydrological system. Beneath the ground, entire rivers flow through darkness, carrying water through 3-dimensional networks of dissolved passages. The sand prairies of northwest Indiana formed on ancient lake beds where post-glacial winds piled dunes over retreating water. As glacial Lake Chicago, predecessor to modern Lake Michigan, drained to lower levels, it left behind flat expanses of lake bottom sand. These former lake beds dried and were exposed to wind, which picked up the loose sand and deposited it inland as dunes. Some dunes migrated and remained active, mobile sand bodies moving across the landscape. Others stabilized when prairie vegetation colonized them, binding the sand with root systems that prevented further movement. The result was sand prairie, a grassland ecosystem growing on sandy soils, drought-prone because of the soil's rapid drainage, supporting plant species adapted to these harsh conditions. Sand prairie differs from tallgrass prairie on clay soils. The plant composition changes. Drought-adapted species become more common. The grasses themselves are often shorter and less dense. Prickly pear cactus, normally associated with southwestern deserts, grows in some Indiana sand prairies, finding conditions suitable in the sandy, droughty soils. Before European settlement, sand prairies covered substantial areas in northwest Indiana. Most were converted to agriculture or succeeded to forest when fire suppression allowed trees to invade. The remaining fragments preserve this distinctive ecosystem, a landscape shaped by post-glacial lakes, by wind-building dunes, by fire maintaining grassland, by plants adapting to soils that hold almost no moisture. Stand in a sand prairie in late summer during drought, and you perceive its harshness. Plants stressed by heat and lack of water, sand hot enough to burn bare feet, vegetation sparse. Yet this apparent harshness supports specialized species found nowhere else. At Pine Hills, nature preserve, sandstone pillars eroded into narrow towers stand separated from cliff faces, monuments to weathering over millions of years. These pillars, sometimes called hoodoos or rock towers, form through a specific erosion process. The sandstone cliff contains vertical joints, fractures that formed as the rock cooled, dried, or responded to tectonic stresses. Weathering attacks these joints, gradually widening them through freeze-thaw cycles, through chemical dissolution, through the simple mechanical action of water flowing through cracks. As the joints widen, they eventually isolate sections of the cliff, creating pillars that stand separate from the main rock face. Once isolated, the pillars erode on all sides, weathering attacking their entire exposed surface rather than just one face. Most pillars thin over time, becoming progressively more precarious as their bases narrow. Eventually, they collapse, the remaining material reduced to rubble at the cliff base. But new pillars form continually as weathering widens other joints. The process creates a landscape of vertical forms, pillars, towers, thin walls too thin to stand independently. The sandstone itself dates from the Pennsylvanian period, formed from sand deposited in ancient river channels. The rock's internal structure, its bedding planes, its variations in cementation, influences how it erodes, some layers resisting weathering better than others. Walking among the pillars creates an odd sense of scale. They're tall enough to seem imposing, yet small enough to walk around. Geological features reduced to almost human dimensions. They will not persist. A century from now, some will have fallen, but their impermanence is part of their nature, evidence that even stone is temporary. The Vincennes Sun Rift, a minor fault line beneath Knox County, occasionally produces barely perceptible tremors as ancient stresses release. Indiana is not known for earthquakes. It lies far from active plate boundaries where most seismic activity occurs. Yet the bedrock beneath the state contains numerous faults, fractures where rock on one side has moved relative to the other side. Most of these faults are ancient, formed hundreds of millions of years ago during tectonic events that have long since ceased. The Vincennes Sun Rift is one such feature, a zone of weakness in the bedrock where movement occurred in the geological past. Today, the fault is largely inactive, but residual stresses remain locked in the surrounding rock. Occasionally, these stresses release through minor slippage along the fault plane, generating small earthquakes. Most are too subtle to feel, magnitude 2 or less, detectable only by seismographs. Occasionally, a slightly larger event occurs, large enough that people report feeling a brief rumble or hearing a sound like distant thunder. These earthquakes cause no damage, no injuries, serving mainly as reminders that the earth beneath Indiana is not entirely static. The bedrock continues adjusting to stresses, continues seeking equilibrium, continues moving in increments too small and slow to notice directly. The Vincennes Sun Rift represents one locus of this adjustment, a fault reactivating periodically as the crust accommodates forces generated by processes occurring hundreds or thousands of miles away. The weight of sediment accumulating in the Gulf of Mexico, the ongoing rebound from glacial loading, the slow movements of the mantle beneath the continent. In the Hoosier National Forest, sinkholes appear suddenly when underground voids collapse, some large enough to swallow entire trees. Sinkhole formation in karst landscapes is an ongoing process, not a historical artifact. Limestone continues dissolving as water percolates through it, creating and enlarging voids. These voids expand upward through a process called stoping. Small collapses at the void ceiling, each failure enlarging the cavity slightly. Eventually, the void approaches the surface, leaving only a thin layer of soil and rock between the cavity and the ground above. This bridge can persist for years, decades, even centuries, supporting its own weight and whatever grows on the surface. Then something triggers collapse. Perhaps heavy rain saturates the soil, adding weight. Perhaps frost action weakens the remaining material. Perhaps the void simply enlarges until the bridge can no longer span it. collapse occurs suddenly, without warning. Ground that appeared solid yesterday contains a crater today, anywhere from a few feet to dozens of feet across. Trees growing above the void tilt into the depression or topple entirely. The sinkhole's bottom may reveal the underlying void, a cave passage now open to the sky, or it may fill with collapsed material, burying the void under rubble. New sinkholes appear every year in the Hoosier National Forest, evidence that the landscape continues evolving, that the ground beneath the forest is not solid, but riddled with voids in various stages of development. Hiking through the forest, you might notice older sinkholes, depressions now partially filled with leaves and soil, trees growing on their slopes, vegetation gradually reclaiming the disturbance. Each represents a moment when the subsurface and surface landscapes intersected, when hidden processes became suddenly, dramatically visible. The ancient Tees River gravels beneath Richmond contain diamonds washed from Canada, microscopic crystals transported hundreds of miles by pre-glacial streams. These are not gemstone-quality diamonds. They're tiny crystals, often only fractions of a millimeter across, visible only under microscope. They formed in Canada's ancient volcanic pipes, regions where volcanic eruptions brought diamond-bearing rock to the surface from deep in the mantle. Weathering released the diamonds from their host rock, and rivers carried them downstream along with other sediment. The Tees River, flowing northwest across Indiana before the Ice Age, transported sediment from source areas that included diamond-bearing regions. The diamonds, being extremely hard and resistant to weathering, survived transport that destroyed softer minerals. When glaciers later buried the Tees River Valley, they preserved these gravels, sealing the diamonds in place. Today, they can be recovered from well cuttings or geological samples, tiny crystalline witnesses to river systems that flowed millions of years before glaciation. The diamond's presence demonstrates enormous transport distances. They originated in Canada, traveled through what's now Ohio and Indiana, covering hundreds of miles before deposition. Their survival demonstrates diamonds' exceptional durability. They passed through multiple cycles of erosion, transport, and deposition without significant damage. Finding them requires patient work, processing large volumes of sediment, examining samples under high magnification, identifying the characteristic morphology and properties of diamond. But they exist. Microscopic treasures in buried river gravels, evidence of ancient drainage systems, and the power of rivers to transport material across continents. At McCormick's Creek, travertine deposits build up where calcium-rich spring water cascades over rock ledges, adding layers of new stone each year. Travertine is a form of calcium carbonate that precipitates directly from water, rather than accumulating as organic material like most limestone. The process requires specific conditions: groundwater that has dissolved abundant calcium carbonate percolating through limestone, then emerging at the surface where carbon dioxide escapes into the air. As CO2 leaves the water, calcium carbonate becomes supersaturated and precipitates, coating whatever surface the water flows over. At McCormick's Creek, springs emerge from the canyon walls and flow down the rock faces. Wherever this water flows, travertine accumulates, thin layers deposited one atop another, gradually building thickness. The deposits often encrust moss and other plants growing on the wet rock, creating fossilized vegetation patterns. Over time, travertine can build substantial structures, dams across streams, terraces on hillsides, even stalactite-like formations where water drips from overhangs. The process continues actively. Visit McCormick's Creek and you see new travertine forming, modern precipitation of ancient minerals, stone being created in real time rather than through geological processes requiring millions of years. The travertine itself is relatively soft when fresh, hardening gradually as it ages. Its color varies from white to tan to rust orange depending on mineral impurities. The formations create their own beauty. Flowing patterns where water sculpted the deposits, textures ranging from smooth to rough, vegetation growing on surfaces where moisture persists. Travertine represents one of the few geological processes visible on human timescales, a reminder that rock formation is not always ancient history, but sometimes contemporary process. The dune and swale topography along Lake Michigan's shore creates parallel ridges marking ancient beach positions as the lake level fluctuated over millennia. Stand on the beach and look inland, and you see a series of low ridges running parallel to the current shore. These are old beach ridges, dunes formed when the lake stood at different levels. As lake levels dropped, whether through climate change, through isostatic rebound as the land rose after glacial ice melted, or through the lake finding lower outlet channels, each former shoreline was left stranded inland. Wind then piled sand along these former beaches, creating dunes that marked the old waterline. Between the ridges lie swales, low areas that were shallow water or wetland when the lake was higher. Today, these swales support different vegetation than the ridges, often wetter conditions, different soil composition, distinct plant communities. The pattern creates ecological heterogeneity, habitat diversity resulting from geological processes. Counting the beach ridges moving inland provides a rough chronology of lake level changes. Each ridge represents a distinct lake stage, a period when the water stood at particular elevation long enough for a dune to form. The most recent ridges near the current shore are youngest, sometimes only decades or centuries old. Ridges farther inland are progressively older, the most distant representing lake levels that existed thousands of years ago. The entire sequence records Lake Michigan's history, its expansion and contraction, its search for equilibrium between water input and output, its response to climate change and glacial rebound. In Perry County, the Anderson River rises from a limestone spring that never varies more than 2 degrees in temperature year-round. This thermal constancy, perhaps fluctuating between 53 and 55 degrees, reflects the spring's source deep in the aquifer system, where seasonal temperature variations cannot penetrate. The Anderson River's origin as a spring rather than as a collection of surface runoff gives it distinctive characteristics. Its flow remains relatively constant throughout the year, buffered by groundwater storage from the droughts and floods that affect surface streams. Its temperature stability creates habitat for organisms adapted to constant conditions, certain fish species, aquatic insects, plants that cannot tolerate the temperature swings common in surface waters. The spring water itself is exceptionally clear, having been filtered through limestone as it percolated from surface to aquifer to spring. Dissolved minerals give the water distinctive chemistry, high in calcium and magnesium from limestone dissolution, often slightly alkaline in pH. The spring's discharge point creates a microhabitat distinct from the surrounding landscape. Constant moisture, stable temperature, unique water chemistry. Vegetation around the spring differs from nearby areas, with species adapted to perpetual wetness. In winter, the spring's relatively warm water, warm compared to freezing air temperatures, creates mist and prevents ice formation even when surface streams freeze solid. The Anderson River flows from its spring origin, gradually warming or cooling toward ambient temperature as it moves downstream, eventually joining larger waterways. But at its source, it maintains the aquifer's temperature, a connection to the underground hydrological system that feeds it. The Muscatatuck Plateau, carved from Mississippian limestone, rises 200 feet above surrounding valleys where softer shales eroded away. The plateau exists as a result of differential erosion. The bedrock is not uniform, but consists of layers with varying resistance to weathering. The Mississippian limestone forming the plateau's caprock is relatively hard, well cemented, resistant to erosion. The shales underlying and surrounding it are much softer, easily eroded by water and weathering. Over millions of years, streams carved away the shales, lowering the valleys while the limestone-capped plateau remained elevated. The result is a landscape of contrasts: flat plateau tops, steep escarpments where the limestone edge is exposed, deep valleys cut into the softer surrounding rock. The plateau's edge shows the limestone cap very clearly, a resistant ledge underlain by slopes of softer material. Water flowing over this edge creates waterfalls where streams tumble from plateau top to valley floor. The plateau itself, being elevated and flat, has different drainage characteristics than surrounding areas. Water doesn't concentrate quickly, creating a landscape of seasonal wetlands and slowly flowing streams. The limestone bedrock beneath the plateau is riddled with karst features: sinkholes, caves, underground drainage. Stand on the plateau top and you stand on a landscape that survived while everything around it eroded away, an erosional remnant demonstrating how rock composition determines topography. At Cataract Falls, the largest waterfall by volume in Indiana, drops 86 feet total over 2 cascades, cutting backward through rock at a rate of inches per century. Cataract Falls is actually 2 separate falls. Upper Cataract Falls drops 45 feet. Lower Cataract Falls drops 30 feet, with a short reach of rapids between them. Together, they represent Indiana's most substantial waterfall by the measure of total water volume flowing over them. The falls exist because Mill Creek flows over resistant rock layers. The water cannot erode them as quickly as the softer rock downstream, maintaining the vertical drop. But erosion continues. The force of falling water undermines the rock at the fall's base, creating a plunge pool. This undermining occasionally causes chunks of the rock ledge to collapse, moving the falls upstream by small increments. The process is slow, measured in inches per century rather than feet per year, but cumulative over geological time. The falls are gradually migrating upstream, leaving a gorge downstream marking their former positions. Eventually, millions of years from now, the falls will erode entirely away as they retreat up to the creek's headwaters. But that future remains distant. For now, water continues falling, mist continues rising from the impact, and the falls continue their work of erosion, cutting backward through limestone and shale one flood at a time, one molecule of dissolved rock at a time, patient work measured not in human lifetimes, but in the deep time that shapes all landscapes. The ancient Illinois Basin beneath southwestern Indiana contains oil and natural gas deposits formed from marine organisms that lived 300 million years ago. These hydrocarbons originated as organic matter, plankton, algae, tiny marine creatures that settled to the seafloor when they died. In environments with low oxygen, this organic material did not decay completely, but accumulated in sediment. Over time, burial under thousands of feet of additional sediment subjected the organic matter to heat and pressure. At specific temperature and pressure ranges, complex organic molecules broke down into simpler hydrocarbons, the oil and natural gas we extract today. The Illinois Basin is a geological depression, a bowl-shaped structure in the bedrock where sediment accumulated particularly thick. Within this basin, source rocks containing organic matter lie adjacent to porous reservoir rocks where hydrocarbons can migrate and accumulate. Cap rocks, Impermeable layers like shale trap the hydrocarbons, preventing them from escaping to the surface. Oil and gas fields in southwestern Indiana tap into these accumulations, extracting fossil fuel that represents stored solar energy from the Pennsylvanian period. The plankton that became this oil captured sunlight through photosynthesis 300 million years ago. That captured energy remained locked in chemical bonds through burial, through lithification, through the entire span of time that brought us from tropical coal swamps to the modern landscape. Now we extract it, burning in hours what took millions of years to accumulate, releasing carbon that has been sequestered underground since before dinosaurs existed. Near Shades State Park, what locals call the Grand Canyon of Indiana, demonstrates water's power to carve narrow channels through solid rock. The term Grand Canyon is generous. These are not mile-deep gorges, but relatively modest channels, perhaps 40 or 50 feet deep in places. Yet their narrowness is striking. In some sections, the canyon walls stand only a few feet apart, close enough to touch both sides simultaneously. Hikers must turn sideways to squeeze through certain passages. The channels formed where Sugar Creek and its tributaries carved through sandstone and shale, following joints and fractures in the rock. Water concentrated along these weaknesses, eroding them preferentially, creating slot canyons rather than broad valleys. The process accelerated during periods of high flow, floods carrying abrasive sediment, glacial meltwater with tremendous volume and velocity. The canyon walls rise vertically from the stream, their faces showing the layered structure of the rock. Bedding plains from ancient river deltas, cross-bedding from underwater sand dunes. Ferns grow from cracks where moisture seeps through the stone. Moss covers surfaces that remain perpetually damp. The canyons create cool, shaded environments even on hot summer days, their depth and orientation preventing direct sunlight from reaching the channel floor. Walking through these passages provides an intimate encounter with erosion's work. You move through the space that water has created, following paths carved by floods and persistent flow, surrounded by stone walls that narrow to arm's width in places. The Bloomington Moraine System contains dozens of kettle lakes formed when buried ice blocks melted, leaving depressions that filled with water. Kettle formation requires specific conditions. A glacier must be stagnating, meaning it's no longer flowing forward, but melting in place. As the ice melts, blocks sometimes become separated from the main ice mass and buried under glacial sediment. These buried ice blocks are protected from direct sunlight by their sediment covering, allowing them to persist for years or even decades after the main glacier has retreated. Eventually, they melt, and the ground above them collapses into the void left by the vanished ice. The resulting depression is a kettle. If the kettle bottom lies below the water table, it fills with water, becoming a kettle lake. The Bloomington Moraine System, marking one pause in the glacier's retreat, contains numerous such features. Small lakes scattered across the landscape, each occupying a depression created by melted ice. These kettle lakes tend to be roughly circular in plan view, reflecting the shape of the ice blocks that created them. Their depths vary depending on ice block size. Some kettles are shallow ponds only a few feet deep. Others are substantial lakes reaching 40 or 50 feet. The lakes support distinct ecosystems, their water chemistry and biology influenced by their isolation. Kettle lakes have no inlet streams, receiving water only from direct precipitation and groundwater, which affects their nutrient levels and species composition. Each kettle lake is a direct legacy of glaciation, a landscape feature that couldn't exist without ice creating the initial depression. At Clifty Creek, fossil hunting reveals complete crinoid stems, ancient sea lilies that grew in colonies across the Mississippian seafloor. Crinoids are echinoderms, relatives of sea stars and sea urchins, that attach to the seafloor via a stem and filter nutrients from the water using feathery arms. The stem consists of disc-shaped segments stacked like coins, flexible enough to sway with currents, yet sturdy enough to hold the organism upright. When a crinoid died, its soft tissue decayed quickly, but the calcite stem segments often remained, scattering across the seafloor, or, if rapidly buried, preserving an articulated position. The limestone along Clifty Creek contains abundant crinoid fossils, some showing complete stems that can be traced segment by segment through the rock. Other beds contain millions of disarticulated segments, the coins scattered and mixed with other sediment, sometimes forming rock layers composed almost entirely of crinoid debris. These accumulations are called crinoid limestone or crinoidal limestone, rock made from the skeletal remains of organisms that lived in dense colonies. The fossils themselves appear as circular impressions in cross-section, cut through a crinoid stem, and you see the characteristic star or flower pattern in each disc. Find one oriented longitudinally, and you see the stem's full length, its segments still connected as they were when the organism swayed above the Mississippian seafloor. The abundance of these fossils demonstrates how common crinoids were, how densely they colonized the seafloor, and how effectively their calcite skeletons could fossilize given proper burial conditions. Mount Baldy at Indiana Dunes has advanced inland by consuming everything in its path, including a buried brick building discovered decades after disappearing beneath the sand. The building's burial demonstrates the dune's relentless migration. Sand accumulated around the structure, gradually covering walls, then roof, until the entire building vanished under advancing dune. For years, it remained buried, hidden beneath tons of sand, its location known to old-timers but invisible to newcomers. Then, as the dune continued migrating, erosion on its trailing edge began exposing the buried structure. First, a corner appeared, then portions of walls, eventually enough that the building became recognizable again. The discovery fascinated geologists and historians. Here was direct evidence of the dune's migration rate, a fixed reference point that allowed precise measurement of advance. The building itself was eventually removed for safety reasons, but its burial and reemergence illustrated the dune's nature as an active geological process. Mount Baldy continues moving inland, currently approaching areas that contain roads and structures. Park managers monitor its progress, aware that the dune will eventually threaten infrastructure. The dune itself cares nothing for human concerns. It responds only to wind, to sand supply, to the physical processes that have been moving it inland for centuries. What lies in its path will be buried, as the brick building was buried, as trees have been buried, as whatever else exists where the dune travels will be buried. Eventually, the dune will migrate far enough that Lake Michigan deposits fresh sand behind it, and the cycle continues. Sand, moving inland in waves, each grain following the same path, beach to dune to eventual stabilization when vegetation finally traps it. At Potato Creek State Park, glacial erratics, boulders carried from Canada by ice, sit incongruously on flat terrain hundreds of miles from their origin. These erratics are typically granite, gneiss, or other crystalline rocks foreign to Indiana's sedimentary geology. They originated in the Canadian Shield, the ancient core of the North American continent, where billion-year-old rocks lie exposed at the surface. Glacial ice advancing across this terrain plucked boulders from bedrock, incorporating them into the ice, transporting them southward as the glacier flowed. Some erratics traveled hundreds of miles from their source, riding within or on top of the ice sheet. When the glacier finally melted, the boulders were deposited wherever the ice happened to drop them, often in locations geologically absurd. Granite from Canada resting on limestone in Indiana. The erratic's size varies enormously. Some are modest rocks weighing a few hundred pounds. Others are massive boulders weighing tons, far too large for any stream to transport, so large that their presence proves glacial transport. The contrast between erratic and bedrock is usually obvious. The boulder is granite or some other igneous rock, hard and crystalline, often pink or gray, completely unlike the sedimentary limestone or shale of Indiana. Geologists identify erratics partly through this lithological difference and partly through their position. Boulders sitting on flat terrain with no nearby bedrock source. Each erratic is a traveler frozen in place, a rock exiled from its homeland by ice, left behind when its transporting glacier melted away. They persist as monuments to glaciation, evidence of ice powerful enough to carry tons of rock hundreds of miles. The Vernon Fork Muscatatuck River drains a watershed containing over 100 documented caves and countless unexplored passages threading through the limestone bedrock. This concentration of caves reflects the region's karst geology, thick limestone formations, abundant rainfall, and conditions favorable for dissolution. The caves themselves vary enormously in character. Some are wet caves with active streams flowing through them, the sound of water echoing from stone walls, formations growing where water deposits dissolved minerals. Others are dry caves, abandoned by the water that formed them, decorated with stalactites and stalagmites accumulated over millennia. Some caves are spacious, with rooms large enough to hold groups of people comfortably. Others are tight crawls, requiring squeezing through narrow passages barely wide enough for a human body. The documented count, over 100, represents only caves that have been explored, surveyed, and reported. Many more exist but remain unknown, their entrances hidden, their passages waiting for discovery. Some caves connect to each other, underground, creating systems that extend for miles. Others are isolated features, small solution cavities, unconnected to larger passages. The concentration of caves in this single watershed demonstrates how extensively dissolved the limestone has become. The rock beneath the surface is not solid but riddled with voids, a three-dimensional Swiss cheese of passages, chambers, and solution cavities. Water moving through this landscape often flows underground rather than across the surface, making hydrology complex and difficult to predict. A stream might disappear into a cave entrance and not emerge for miles, its subsurface course unknown. At Tippecanoe River State Park, ancient sand dunes stabilized by vegetation reveal the power of post-glacial winds that once swept the region. These are not coastal dunes formed by current Lake Michigan winds, but interior dunes formed thousands of years ago when the landscape was freshly exposed after glacial retreat. The conditions then were ideal for dune formation: abundant sand from glacial outwash, sparse vegetation unable to bind the soil, strong winds with unobstructed fetch across barren terrain. Wind picked up sand from outwash plains and river valleys, carrying it until obstacles slowed the wind enough for sand to drop. The dunes built up grain by grain, migrating across the landscape until vegetation finally colonized them. Once plant roots penetrated the sand, binding it together, the dunes stabilized. Today, they appear as gentle swells in the terrain, low ridges covered with forest or prairie. The underlying sand is obvious in road cuts or eroded banks, pure quartz sand identical to beach sand, poorly suited for agriculture, rapidly draining. These fossil dunes mark a brief period, perhaps a few thousand years, when the landscape was unstable, when wind could move sand freely before vegetation re-established itself. The dunes themselves preserve a record of wind direction, their shapes reflecting the prevailing winds that built them. Study their orientation, and you reconstruct the wind patterns of the late glacial period, understanding how air moved across a landscape that no longer exists, across terrain that has since been transformed by vegetation, by soil development, by the gradual re-establishment of ecosystems. The Huron Lake bed lies buried beneath Elkhart County, a geological feature that once held glacial meltwater 20 feet deeper than modern Great Lakes levels. Huron Lake, not to be confused with Lake Huron, was one of several glacial lakes that existed during ice retreat. These lakes formed when meltwater accumulated behind ice dams, filling basins faster than the water could drain away. Huron Lake occupied a depression now filled with more recent sediment, its former shore positions detectable through beach ridges buried under till and outwash. The lake's depth, substantially greater than current Great Lakes, reflected both the volume of meltwater being generated and the fact that outlet channels were still ice-blocked, preventing drainage. When these outlets finally opened, or when ice dams failed, the lake drained rapidly, sometimes catastrophically. Huron Lake dropped to lower levels, eventually disappearing entirely as drainage improved and the landscape stabilized. Today, its former basin exists as flat terrain, the lake bed buried under post-glacial deposits. Drill through these deposits and you encounter lake sediments, fine clay and silt that settled from still water, layered deposits recording the lake's existence. These sediments differ from glacial till in their sorting and stratification. Lake deposits are finer, more uniform, showing the quiet accumulation characteristic of still water environments. The buried lake bed influences modern hydrology. Its fine-grained sediments can form aquitards, layers that restrict groundwater flow, affecting well yields and drainage patterns. The lake itself persists only in the geological record, in buried sediments and shoreline features, evidence of a time when the landscape was transitioning from ice-covered to ice-free. In Martin County, Buda Karst preserves pristine cave ecosystems where blind beetles and springtails complete life cycles never exposed to sunlight. These caves remain largely protected from human disturbance, allowing their ecosystems to function as they have for thousands of years. The organisms that inhabit them are highly specialized, adapted to conditions found nowhere on the surface. Blind beetles have lost their eyes entirely, useless organs in perpetual darkness, eliminated through generations of natural selection, favoring individuals who didn't waste energy growing and maintaining vision. The beetles navigate by touch and chemical sensing, detecting prey through vibrations and scent. Springtails, tiny arthropods related to insects, feed on fungi and bacteria growing on cave walls, forming the base of the cave food web. These organisms in turn become food for beetles, spiders, and other predators. Energy entering the system comes primarily from outside, organic material washed in during floods, guano from bats that roost in the caves, roots penetrating from the surface. The ecosystem operates on an energy budget far smaller than surface ecosystems, with organisms adapted to long periods between meals. Growth rates are slow, lifespans extended, reproduction infrequent. The cave environment is stable, temperature constant year-round, humidity near saturation, darkness absolute. This stability has allowed highly specialized species to evolve species that could not survive the temperature swings and light exposure of surface habitats. Buddha karst's protection ensures these ecosystems remain intact. These species continue existing in darkness, adapted to conditions so unusual that they seem alien, yet are simply the Earth's underground frontier where life has found ways to persist. The limestone solution valleys of southern Indiana, formed as underground drainage, captured surface streams, leaving dry valleys that flow only during exceptional rains. These valleys appear normal. They have the shape and gradient of stream valleys, the meandering pattern characteristic of water-carved channels, but they contain no permanent streams. The valley floors are dry, grown over with vegetation, showing no evidence of regular water flow. What happened? The streams that carved these valleys encountered limestone bedrock, began dissolving it, and eventually created underground channels more efficient than the surface channel. Water preferentially followed these underground routes, abandoning the surface valley. The valley itself persists as a relic feature, testimony to a time when surface drainage was active. Only during extraordinary rains, when underground channels can't accommodate all the runoff, does water return to flow through these dry valleys, temporarily recreating the streams that originally carved them. The phenomenon demonstrates karst hydrology's complexity. Drainage that seems obvious from topography actually occurs underground, through passages invisible from the surface. Walk through a solution valley, and you walk a stream bed without a stream, following the course water carved but no longer occupies. The disconnect between topography and hydrology can be disorienting. Everything about the valley suggests water should flow through it, yet it remains dry except during rare floods. This characteristic creates challenges for development and agriculture. A valley that appears safe from flooding can suddenly fill with water when underground drainage reaches capacity, catching those unfamiliar with karst hydrology by surprise. At Ferdinand State Forest, the Mitchell Plateau's resistant sandstone caprock creates flat-topped hills rising from dissected limestone valleys below. The plateau demonstrates inverted topography. What was once a valley fill is now elevated terrain. During the Pennsylvanian period, rivers deposited sand in their channels, sand that eventually lithified into sandstone. This sandstone, being harder than the surrounding limestone, resisted erosion more effectively. Over millions of years, streams carved away the limestone, lowering the valleys, but the sandstone-filled ancient river channels remained elevated. The result is a landscape where old valleys now form ridges, a reversal of the original topography. The plateau's edge shows this structure clearly. Sandstone caps overlying softer limestone and shale. The cap protects underlying rock from erosion, maintaining flat plateau tops while surrounding areas erode into valleys and hills. Where streams have cut through the sandstone cap, erosion accelerates in the softer rock below, sometimes creating amphitheater-shaped valleys. The plateau forest differs from valley forest. Different soil moisture, different exposure, different species composition. The flat plateau tops drain poorly, creating seasonal wetlands. The slopes and valleys drain rapidly, supporting mesic to dry forest types. This topographic diversity creates habitat complexity, supporting high biological diversity within relatively small areas. The plateau itself will eventually erode away. Streams will continue cutting backward into the cap rock, isolating outliers, gradually removing the resistant sandstone until nothing remains. But that process requires geological time, millions of years of patient erosion, and for now the plateau persists, a remnant of ancient river systems transformed through differential erosion into uplands. The ancient Louisville limestone beneath Clark County contains coral heads 3 feet across, solitary reef builders from warm Devonian seas. These are not the branching corals typical of modern reefs, but massive, dome-shaped structures built by solitary coral polyps over their lifetimes. Each coral head represents decades or centuries of growth. The polyp secreted calcium carbonate, building its protective skeleton, adding layer upon layer as it grew. The resulting structure resembles a mushroom or dome, sometimes reaching substantial size. 3 feet across represents an old individual, possibly living for a century or more in the Devonian Sea. When the polyp died, the coral head remained, a permanent structure on the seafloor that could be colonized by other organisms or buried by sediment. The Louisville limestone preserves these structures in remarkable detail. The growth lines remain visible, the surface texture showing where the polyp lived, sometimes even evidence of damage and regeneration during the coral's life. Finding one is like encountering a monument to a single organism's lifetime, a 3-foot testimony to decades of patient growth in tropical waters 380 million years ago. The limestone containing these fossils is quarried in places, and occasionally a coral head is exposed during excavation, standing out from the surrounding rock. These discoveries remind us that limestone is not simply stone, but accumulated biological material, the compressed remains of countless organisms that built calcium carbonate structures in ancient seas. The coral heads are the most visible fossils, but the matrix surrounding them contains millions of smaller organisms, brachiopods, bryozoans, crinoid fragments, even microscopic foraminifera, all contributing to the limestone's bulk. In the Jasper-Pulaski Fish and Wildlife Area, wet prairies flood seasonally, just as they did when mammoths grazed here 13,000 years ago. These prairies occupy flat terrain with poor drainage, clay soils that shed water slowly, creating conditions where spring rains and snowmelt accumulate in shallow sheets across the landscape. During wet seasons, the prairies become extensive shallow wetlands, water standing inches to feet deep, creating habitat for waterfowl and shorebirds. As summer progresses and evaporation exceeds precipitation, the water gradually recedes, exposing mudflats and then dry ground by late summer. This cycle, flooding in spring, drying in summer, has persisted for thousands of years. During the late glacial period, when mammoths and other megafauna inhabited Indiana, these same prairies flooded seasonally, providing water sources and lush vegetation for grazing. The mammoths themselves are long extinct, disappeared around 10,000 years ago when climate change and human hunting pressure combined to eliminate North America's megafauna. But the wet prairies remain, essentially unchanged in function, if not in detailed species composition. The grasses and sedges that dominate now may differ from those the mammoths grazed, but the basic ecology persists: seasonal flooding, prairie vegetation adapted to wet-dry cycles, habitat supporting migrating waterfowl. Jasper-Pulaski is particularly famous for sandhill crane migrations, thousands of cranes stopping here during spring and fall passage. The cranes use the wet prairies much as ancient birds used them, finding food and shelter in landscape that has remained functionally similar across the entire span of post-glacial time. The Huntington Reservoir drowned the Wabash River Valley where Native Americans once quarried flint from exposed bedrock. Before the reservoir existed, the Wabash flowed through this valley in its natural state, and in certain locations, bedrock containing flint nodules was exposed along the riverbanks. Flint, a form of microcrystalline quartz, occurs as nodules within limestone, formed through silica precipitation in cavities or through replacement of carbonate with silica. The flint breaks with sharp edges, making it ideal for tools, spear points, scrapers, knives, any implement requiring a sharp edge. Native Americans recognized this quality and quarried flint where it was accessible, returning to known outcrops generation after generation. Archaeological evidence shows intensive use of these flint sources, with tool-making debris scattered across quarry sites. Then in the mid-20th century, engineers built the Huntington Dam. The reservoir filled, and these quarry sites vanished beneath water. Today, they exist dozens of feet underwater. The bedrock that once supplied material for countless tools now submerged. Occasionally, during extreme drawdowns when the reservoir drops to unusually low levels, portions of the old valley emerge, briefly exposing landscapes that have been underwater for decades. These emergence events sometimes reveal archaeological material, ancient tool-making sites temporarily accessible again before rising water covers them once more. The reservoir serves its intended functions: flood control, water supply, but its creation meant the loss of both natural river valley and archaeological sites, landscapes and history drowned underwater held behind a dam. At Cedar Canyon, winter ice formations build cathedral-like structures 40 feet high where seeping groundwater freezes in layers. The canyon's walls seep water year-round, groundwater emerging where permeable layers meet impermeable ones, moisture that flows down the rock face in thin sheets. During warm months, this water simply flows, supporting moss and ferns. But in winter, when temperatures drop below freezing, the seeping water freezes upon contact with the cold rock, forming ice. Each freeze cycle adds a layer, ice accumulating drip by drip, freeze by freeze, building upward from the canyon floor and downward from seepage points on the walls. The resulting formations are spectacular: columns of ice 40 feet tall, frozen waterfalls, delicate curtains of ice hanging from overhangs, massive frozen flows coating entire cliff faces. The ice is often crystal clear, free of the air bubbles that make pond ice opaque. Sunlight penetrates it, creating blue tones in the thicker sections. The formations grow throughout winter, accumulating mass with each cold night, each seepage event that freezes. By late winter, Cedar Canyon can contain ice structures large enough to dwarf the people who come to view them. Then spring arrives, temperatures warm, and the ice begins melting. The structures thin, weaken, and eventually collapse, chunks of ice tumbling to the canyon floor where they melt into pools. By late spring, no trace remains. The ice has returned to water, flowing away, leaving the canyon bare until next winter when the cycle begins again. The ice formations are entirely ephemeral, existing for a few months annually, yet their scale and beauty make them seem permanent. They are winter's architecture, structures that exist only when conditions allow, vanishing when seasons change. The bedrock topography beneath Indianapolis follows ancient river channels now buried under 200 feet of glacial sediment. Before glaciation, rivers drained this region following bedrock valleys carved over millions of years. These valleys were substantial features, hundreds of feet deep in places, miles wide, the result of persistent erosion cutting through sedimentary rock. Then glaciers advanced, filling these valleys with till as the ice melted. The sediment accumulated to enormous thickness, completely burying the pre-glacial topography. Today, Indianapolis sits atop this glacial fill, its surface essentially flat, showing little evidence of the valleys buried below. But drill down through the glacial deposits, and you encounter the original bedrock surface with its peaks and valleys intact. These buried valleys influence modern hydrology. They often contain coarse sediment deposited by pre-glacial rivers, material that now serves as aquifers. Wells drilled into buried valleys typically yield more water than wells drilled into areas where bedrock stands high. The buried topography also affects engineering. Buildings constructed where the bedrock surface lies deep require different foundation techniques than those where bedrock is shallow. Geologists have mapped this buried landscape using well logs and geophysical surveys, reconstructing a terrain that no one has seen since before the Ice Age. It's a ghost landscape, preserved beneath the fill that created the modern surface, a record of Indiana as it existed before glaciation transformed it entirely. In Gibson County, Oxbow Lakes mark abandoned river channels where the Wabash changed course, creating crescent-shaped water bodies. Oxbow formation is a natural consequence of meandering. As a river's curves become more pronounced, the meander neck becomes progressively narrower. Eventually, usually during a flood when the river runs high and fast, water cuts through the narrow neck, establishing a new, shorter channel. The old meander is abandoned, cut off from the main flow, creating a crescent-shaped lake. The lake persists for decades or centuries, gradually filling with sediment carried by floods that overtop the main channel. Eventually, the Oxbow fills completely, becoming a wetland, then eventually dry land, detectable only as a subtle swale in the landscape or by vegetation patterns that reflect the wetter soils. Gibson County's Oxbow Lakes exist in various stages of this progression. Some are open water, clear crescent lakes separated from the Wabash by narrow levees. Others are partially filled, shallow wetlands choked with vegetation. Still others are completely filled, visible only as curved depressions in farmland. Each oxbow represents a moment in the river's history, a meander that grew too tight and was cut off. Together, they map the river's wandering, its former positions recorded as lakes scattered across the floodplain. The oxbows themselves support distinct ecosystems. Being still water, they accumulate organic material, creating rich habitats for fish, waterfowl, and aquatic plants. Some oxbows maintain connection to the main channel during floods, receiving fresh inputs of water and fish. Others are completely isolated, their fish populations remnants from when the channel was active. The lakes age slowly, each flood adding sediment, each year's vegetation contributing organic material, the gradual filling that will eventually erase them. The northern Indiana moraine complex contains deposits from at least 6 separate glacial advances, each leaving distinct mineral signatures that geologists can identify and correlate across the region. Each advance represents a separate episode when ice flowed across Indiana, carrying its load of rock and soil scraped from bedrock farther north. The source areas varied between advances. Sometimes the ice flowed from a particular region of Canada, carrying rock types characteristic of that area. Other times, different flow paths brought different materials. These variations created till layers with distinct characteristics, different mineral compositions, different colors, different ratios of sand to clay. Geologists can identify these differences in road cuts, quarries, and drill cores, using them to determine how many advances occurred and in what sequence. The 6 advances recognized in northern Indiana represent hundreds of thousands of years of Ice Age history, periods when climate cooled and glaciers advanced, separated by warmer interglacial periods when ice retreated. Each advance bulldozed and buried evidence of previous advances, but careful study reveals the multiple layers, each telling its part of the story. The deposits stack like pages in a book. Though unlike a book, lower pages can be missing where erosion removed them, or pages can be out of order where glaciers reworked older deposits. Reading this record requires careful observation, patient correlation between widely separated locations, understanding how glacial processes can both preserve and destroy evidence. But the effort reveals deep history, the rhythm of glacial advance and retreat, the changing climate patterns that drove these cycles, the enormous time spans involved in reshaping a landscape through multiple episodes of ice coverage. At the southernmost tip of Indiana, where the Ohio and Wabash rivers meet, water flowing past has carved its course for over 10 million years, longer than humans have existed as a species. This confluence represents one of the oldest persistent landscape features in Indiana, a junction maintained through enormous spans of geological time. While the exact position of the confluence has shifted, while the rivers themselves have deepened their valleys and changed their channels countless times, the basic pattern has persisted. These two major waterways meeting at approximately this location. The confluence predates the Ice Age, predates the Pleistocene entirely, extending back into the Pliocene and possibly earlier. Over those millions of years, the land has risen and fallen through tectonic processes. Sea levels have fluctuated, climates have cycled through warm and cold periods, and still these rivers have continued flowing, continued meeting, continued moving water toward the Mississippi and ultimately the Gulf of Mexico. The water passing the confluence today will reach the ocean in weeks. The water that passed here 10 million years ago reached oceans that no longer exist in the same configuration. Yet the rivers persist, older than the ice that reshaped the landscape, older than most of the topographic features surrounding them, ancient systems that have outlasted almost everything except the bedrock they flow through. Stand at the confluence, and you stand at a place where geography has remained essentially unchanged longer than humans have walked upright, where rivers have been meeting since before our species existed, where water has flowed toward the sea through times so remote they seem almost incomprehensible. The rivers themselves care nothing for this history. They simply flow, responding to gravity, moving water from high ground to low, following the same physical principles that have governed their behavior across all those millions of years.